Okay, welcome everybody to this second day. And the first lecture this morning will be delivered by Francesca. And so please.
Thank you. Okay, so yesterday we left off at the hints of a definition for Carnot groups. So today we're going to see Carnot groups. So the idea is that we were looking at, G, which was a connected and simply connected nilpotent Lie group. So actually, I always mean I look at the Lie algebra, and that was stratifiable. So the idea is that Lie of G can be expressed as a direct sum decomposition. We saw using the dilations, and the eigenvalues are positive integers starting from 1, and the first layer bracket generates. So what we're going to do is to fix a norm on V1 and consider the subbundle induced by V1. So we're going to denote this by delta. So this is a subbundle with delta at G being the push forward of V1 for any point. And so basically, I'm going to measure any vector at delta of G using this left invariant idea of the norm. So I think I'm getting the inverse right. V, where this one is the norm on V1, seen as a subspace of TEG. Right. So as I mentioned yesterday, I'm thinking of having just a Riemannian metric on the first layer. That's the idea. So then I can treat the whole G as a metric space using this norm on the delta subbundle, where for any x and y in G, I'm measuring the CC distance as the infimum of the length computed with this norm of gamma. Now, these gammas, okay, let's write it. Gammas are joining x and y. They're absolutely continuous, and gamma dot at t, at each t, is an element in delta gamma of t for almost every t. So basically, I can measure this length because I'm restricting to considering those curves that can be measured. So I'm just looking at the curves whose tangent is in the correct subbundle. So actually, the real question is, well, can any two points in G be connected via one of these curves, special curves? And the answer is yes, as long as delta is bracket generating. So if you remember, one of the generating, the strong condition on the stratification was that V1 was bracket generating. Now, this can be generalized to consider manifolds that are not groups, where you just have a subbundle, which is just a subbundle, and then you require the subbundle to be bracket generating, then that can be used to create a DCC, CC metric space. So CC stands for Carnot Theodori. Another name for these metric spaces is sub-Riemannian. So sub-Riemannian because i.e. you have a Riemannian metric on a subbundle. So you don't have the metric on the whole tangent bundle, you have the Riemannian metric only on the delta. Now, the crucial thing that is going to mess up with all our plans, especially for the Rham complex, is that the fact that you are restricting yourself to considering a subbundle means that these, so I'm going to call them admissible or horizontal directions. So in our case, we have a stratification, so it's V1, which is a subspace of G. Means that if I want to go along, so in our example, in the angle example, we had these two brackets. So this means that only in this setting, only x1 and x2 are allowed. So they are admissible, which means that can only move along x1 and x2, which also means that I'm not allowed to differentiate along anything else. So if I do df, so I take f, which is a smooth function, and I do the differential. So this, you can think of this as a one form, and I express this in terms of this left invariant basis, then x1f theta 1 plus x2f theta 2 plus x3f theta 3 plus x4f theta 4, right? As you would expect. This is all fine and nice, but even if I write it in this way, I can never do just x3. So even though I write this, I mean x1, x2 minus x2, x1. And even if I write x4, I mean x1, x1, x2 minus x2, x1, x2. Which means, so there is a whole theory of homogeneous orders of operators. Even if I write x3, this is a second order differential operator. And this one is third order. Okay? So this is going to mess things up. So in Riemannian geometry, you have your df. This is order 1, because it is. In this case, it's not. Okay? So this is going to become the origin of all our problems. So, and the fact that it's a stratification will enable us to encode these orders through the weights. Right. Any questions? So the fact that we encode the homogeneous structure is separate from the sub-Riemannian space. So one thing, maybe an example. So I take this as an example. So in this case, I mean, so this looks like the angle group in the sense that x1, x2 is equal to x3, and then x1, x4, x3 is equal to x4, but also x5 is equal to x6. So I don't want you to think that if I have a Lie group, I can only put a sub-Riemannian structure only if it's a stratifiable group, because this is not the case. So this group, so we saw that if it's stratifiable, then the lower central series, the incremental steps of the lower central series coincide with the direct sum decomposition. So I would have to get that G0, which is everything, mod G1. So in this case, this would be the elements that are not bracket of anything. So it's isomorphic to this. This should be my V1. However, you can see that this is not homogeneous because this would mean that x1, x2 is equal to x3. So this would have weight 1. But then x3 would have weight 2 necessarily. However, x4 would have weight 3 on one hand, but weight 2 on the other. And this is a very quick way of seeing if a group is stratifiable or not. So in this case, this is not stratifiable. It does have a homogeneous structure, so you would be able to give weight 1 to x1, x2, and x5, and then G2 to x3 and x6, and then G3 to x4, because then x1, x2 goes into x3, and then x5, x6 goes into x4. So 1 plus 2 gives 3, and 1 plus 2 gives 3. So this works. So this is a homogeneous structure. But the first layer does not bracket generate, so it's not a stratification as we expect. But this doesn't stop us from being able to put a sub-Riemannian structure. So I can put a Riemannian metric on the horizontal distribution generated by this bracket generating subspace. So I can put a metric on this delta, which is not G1, and this would give me a sub-Riemannian manifold, but it's not as nice as we would like, because the homogeneous structure does not correspond to the stratification. So the sub-Riemannian, they're not compatible. And this creates a whole range of other problems that we're not going to consider. But just because a group is not stratifiable doesn't mean that it cannot be sub-Riemannian. Okay. That being said, we're going to consider differential forms now. So everything I'm gonna discuss until I say so in this relies on a homogeneous structure. You can think of a stratification. Like nobody's stopping you for thinking this is just a stratification, but this holds for any homogeneous structure. So we said that we are considering G as TEG, but also as the left invariant vector fields of G. So we are going, so this is a differential geometry construction, okay? So this is different from sub-Riemannian topics. So I am introducing a scalar product on G, and we fix, so we fix a north orthonormal basis, xi's for G, which is adapted to the homogeneous structure. I'm going to say the stratification. So the direct sum decomposition. What do I mean by this? I just list them, and if the first subspace has dimension M1, the first M1 vectors span V1. Then I have the next ones. These span V2 and so on. So this means that just considering this basis means that the subspaces, so in this direct sum decomposition, are orthogonal. Okay, so that's how we construct this scalar product, basically. So we are going to, differential forms. So we're going to consider the dual space of G. So this is the space of homomorphisms between G and R. You can also think of this as the linear maps thing from G to R. And so this is usually referred to as the space of one covectors. As we have seen, so it works exactly in the same way as with left invariant vector fields. I can think of these as one forms that are left invariant. So using the scalar product, we can introduce the dual basis to this orthonormal basis that we considered. So we have theta i's as the dual basis of xi that we constructed right before. Simply by putting theta I on xj is just the delta ij. Okay. And so this gives me so the theta i's are an orthonormal basis of G star, and it's still adapted to the filtration, to the stratification. So using these, this is linear algebra, I can construct the space of antisymmetric tensors both on G and on G star. So I'm going to just write lambda G as the span over R of the xi1 wedge xik with xij in G, and lambda k G star as the span theta I1 theta ik in theta ij in G star. So this, I can do this for any vector space G. So it's not that big of a deal. So the idea is that even in this space of k vectors and k covectors, I can extend the original scalar product that I had on G and G star simply by imposing alpha 1, alpha k, beta 1. So I'm writing it for covectors, but it's the same for vectors. So this is simply the determinant of the matrix given by alpha I, beta j, ij. So there is a standard way of extending just the scalar product on G and on G star to the exterior Lie algebra. of both. Right. So the idea is that this makes things easier because if I have an orthonormal basis xi, orthonormal basis of x, and then theta i's its dual, which is an orthonormal basis of G star, then these behave like an orthonormal basis. Sorry, and theta I1, theta ik are an orthonormal basis of lambda kg and lambda kg star respectively. Right. And yeah, fine. We don't need to know so basically this is just to set the notation and the fact that we need a scalar product in this construction. Right. We're gonna need two duals. So the dual, as you would expect, and we're going to need also the Hodge star dual. So the Hodge star dual is actually easier than you would expect. So you need a concept of an orientation. So we have Hodge star duality. So this is boring. Sorry. So I have two bases, B1 and B2, and we say are co-oriented if the map of change of coordinates has positive determinant. So this means there are two equivalence classes on the space of all bases. So when I say an orientation, I mean I am given a basis and then I assign a +1, a positive or a negative characterization of the basis. So this makes, for me at least, this makes more sense if I think of a basis as a volume covector or vector. So if I have xi as a positive basis of G, then of G, then the idea is that the order of the elements of the basis counts. So in the same way, I would expect the order in this of the elements in this covector to count. Okay, so if I assign just the list, so this I mean x1, x2, xn as a positive, because I like this, it's nice. I would not, so x1, x2, x1, x3, and so on would be negative because I'm switching, right? This is antisymmetric, right? So this is minus the positive vector that I had. So for me, it's easier to think of a positive basis as I like an order. So I put the elements of the basis one after the other, and I call this the positive n covector or n vector. And then the negative ones are the ones that will depend on the sign of the permutation of the indices, right? So this is the idea. So the sign, okay, so the sign of the determinant of the change of basis coincides with the sign of the permutation that you would expect. Okay, so I think the easiest way of like to think about this is you take an n vector and then you look at the sign of the permutation. So what is this Hodge star operator? So it is a linear map. So it maps k vectors, or k covectors is the same, to n minus k vectors or covectors. And you define this, I'm using, oh, it's fine. V wedge star W. This is defined as V W of the volume, the positive volume n vector that you're considering. And this is for any V and W in lambda kg. So just to double check, so if it's a map from k vectors to n minus k, so this would be n minus k, this would be k. So if I wedge it, I get an n vector, which is a scalar times the volume vector, okay? So that checks out. And this is just, you take this as just the definition. So in our example, so the angle, yes, the one I decided to be positive. Yeah, I need to fix it, yeah. And then, yes, yeah. Right, so, in this case, so the angle, it doesn't mean that it's just the angle, it's just a four-dimensional, like this would, even if I didn't have the brackets, this would be the case. So I claim that the Hodge of x1 is simply x2 wedge x3 wedge x4, but the Hodge of x2 is minus x1 wedge x3 wedge x4. And this is because I'm claiming the positive basis, positive orthonormal basis would be x1 wedge x2 wedge x3 wedge x4. Okay. So in this case, I would have, so I need to check. So I check it on the element of the basis. So if I do x1 wedge Hodge x1, by definition, this should be x1 scalar product with x1 volume. So this should be just x1, x2, x3, and x4. So that checks out. And then I need to also check the other ones. But the fact that I am taking this to be an orthonormal basis, all the other elements will give me a 0. So this would give me x1 with x2. This would give me an x1 with x3. And then these would give me an x1 with x4. So these are all 0. So this means that Hodge x1 behaves simply like x2, x3, x4. Okay. Then I leave it as an exercise to check that if I try to put Hodge x2, then I get the minus, because there is going to be an exchange between two vectors that gives me the minus. Okay, same thing works for covectors, as you would imagine. And it is much easier to work with this sort of orthonormal basis of vectors and covectors, as you've seen here. So basically, up to a sign, if I'm working with orthonormal basis and orthonormal vectors, I'm gonna have just I need to get this. I'm gonna get this one. So the complement basically such that xi1 wedge xik xj1 xjn minus k is equal, or is a positively oriented basis. Okay, let's so I can permutate these indices to get the volume form that I like. Right. I'm not gonna do the dual because oh no, I need it. Okay, fine. This is similar to what we saw before with the dual basis. So so I apologize in advance because there's a lot of stars. The so I'm gonna try and use the hashtag for the dual map. So in this case, I'm not going in the opposite, in the complementary dimension. I'm going same dimension, but on the dual space. So I get a k vector and I spit out a k covector just by imposing that the action of the covector on any vector is going to be just the scalar product between v and w. This is the definition. And the same thing goes in the opposite direction. So if I have a covector and I want to spit out a vector, then I can do so by just imposing. So this is that for any k covector, the action on alpha hashtag is going to be the scalar product between beta and alpha. Okay? Just the duality, as you would expect. Right. We're ready to define left invariant forms. So left invariant forms, as you would, so for vector fields, we were push forward, and for forms, we're pulling back. Left invariant forms. So there is no standard notation, so I'm gonna use a random one. So omega L K of G is the space of left invariant K forms on G. And this is defined as omega in omega kg such that the pullback through a left translation, the stars multiply, keeps the form constant. And this is, sorry, for all G in G. This is gonna play the same role as, so if you've done differential geometry, you have your dx dy basis for the forms, for smooth forms in R2, for example, abelian R2. And then you can see if you pull back with the left translation in R2 plus, then these are left invariant. So please think of left invariant forms as constant coefficients, okay? Yeah, I mean, if you were to put a function, then you're evaluating the function somewhere else. So that would change. That would make it not left invariant, okay? Right. Now, another thing, So I would like to point out that we're doing exactly the dual considerations that we did for the Lie brackets. So left invariant vector fields, we needed to check that it was a Lie algebra. So we needed to check the bracket. In this case, we're checking whether the left invariant forms are a complex. So whether the differential, so is it true that d of omega k L G is included in omega k plus 1 L of G. So if the differential of a left invariant is still left invariant. And so here I'm assuming omega is KLG and its differential is not 0, because otherwise I'm not saying anything interesting. So the idea is that, okay, so I do the pullback of d omega. Is this the same as d omega? So exactly in the same way that the push forward commutes with a bracket, I know that the differential commutes with a pullback. So this differential commutes with the pullback. So this is simply dLg pullback of omega. Omega is a left invariant, so this is d of omega. So I'm happy. This is a complex, okay? So this, if I stay in the space of left invariant, if you're interested in these things, in more algebraic things, the fact it's not a case, just a random thing, that the space of left invariant differential forms is a complex, because this coincides with the space of k covectors, as we saw, exactly the same way. And this, using the differential on the space of covectors, the serial Lie algebra of a Lie algebra, is called the Chevalier-Eilenberg complex. So there is a cohomology, and if you study Lie algebra cohomologies, this is everyday work that you do. So this is the basic thing. So if you limit yourself to left invariant forms, then you compute what is known as the Lie algebra cohomology. We're not interested in the Lie algebra cohomology. We're considering the Rham cohomology. Okay. Good. Now, we like these forms because they have constant coefficients. Can they be used in the same way that you would do for omega, for example, in omega k in R2 plus? This would be the space of f dx. Well, let's do one forms. F dx plus g dy with f and g smooth functions. I would like to do the same, and I can do this using these left translations. So given f smooth function and theta a k covector, then I can consider theta tensor product with f as an element of omega k g by imposing that theta tensored at f evaluated at g, this is simply f at g, dlg inverse pulled back, and I'm using another of theta. So here I should have extended the definition of the pullback to k covectors. I assume you're familiar with it. So here I am pulling back the k covector by left translation. So this just means that there is an isomorphism between the space of homomorphisms between lambda kg to C infinity G, which is isomorphic to lambda kg star tensored with C infinity G to the space of smooth K forms. What am I saying? So this is a bunch of isomorphism, but the idea is that this justifies the idea that omega kg is simply a C infinity G module over real K covectors. So in the same way that you would see one forms as f dx1 plus g dxy, you can think of omega 1g. So for example, in the angle group, I can think of omega 1g. I called it E, sorry, as f1 theta 1 plus f2 theta 2 plus f3 theta 3 plus f4 theta 4 with fi's as smooth functions. So we're very happy about this, okay? So left translations work the same way that you would expect with abelian Rn, and I can move, yes. E. This is G. This one. This is omega L. This is left invariant. No, you're tensoring with this. Once you tensor, you're adding the function, and that's all smooth. Yeah. Oh, yes. So this is omega KL, and this, once you plug some function, this is everything. So just to reiterate, left invariant, constant coefficients, and it's the same way that you would think of smooth functions in Rn, in charts, but we have a global charts because we work in Rn. Right, so we are ready to, what time is it? To do weights of forms. So now we talked about weights, but we only introduced weights for the elements of G, so vectors. Now we're ready to, so we need to extend it to covectors, to K covectors, and then to all smooth forms, okay? So the quickest way of getting this, so this is the definition. So you extend this by saying, okay, the dilation through lambda of omega, omega being a smooth form. So this is, so you dilate a form, you get a form. I evaluate it at the point G on the vector fields x1 to xk. Now, this is by definition omega evaluated at G to the dilated vector fields or vectors. We're working mostly with left invariant, so it's the same. So the lambda is getting, so this is the definition, gets spat out by the vectors. So because I do know how to dilate the vectors. So and by this, I'm not going to prove it. This implies that if I do the dilation of the wedge of two forms, then this is delta lambda of the first, wedge delta lambda of the second. Right. I'm going to make it way more explicit than this, okay? So think of more explicit. Consider, what are we going to consider? We're going to consider left invariant, one form on a stratified group. Again, this works for any direct sum decomposition that comes from a homogeneous structure. I have my direct sum decomposition, then a left invariant one form will be, now I'm going to make it extremely easy. I mean, you can, I don't want to accumulate notation. So I'm just taking a one form that can be expressed as the sum of theta i's, and each theta I is in VI. So each theta I is in is the dual, is in the dual of VI. Okay. So you can make it as thorough as you want. So for each I between 1 and S, I'm dilating theta I, and I'm computing, so the fact that I'm computing at a point, it doesn't make much difference, but I'm going to keep it. So it's a one covector, a one form. So I just need one xj to evaluate this. So this is by definition theta I computed at G dilating xj. Now, I'm taking xj to be in Vj. So by construction of the dilation, I'm dilating xj by lambda to the j. So this spits out lambda to the j of theta I xj, basically. This is left invariant, so, right? So if you remember, so I have an orthonormal basis that I'm using, which means that theta I xj is equal to 0 if j is not the same as I, which means that the only non-trivial something that I get is going to be when j is equal to I. So this means that delta lambda of theta I is equal to lambda I theta I. Which means that in the same way that I had, so I have an element x, a vector x, in VI it has weight I, its dual will have the same weight. So, yeah. And then I can use the wedge. So there are different ways of thinking about this, but basically what is happening for functions, because functions are zero forms. What is the weight of a function? I'm not evaluating it on anything. So if I dilate a function, I'm gonna get nothing. This is f as a one form. So this means that the weight of functions is 0. You can also think of, if I do the weight of f of theta I, this can be thought of as the weight of f composed with theta I, and I already know that this should be the weight of f plus the weight. Sorry, I didn't do this. Right. Okay, I'm finished writing. So this is the same as the weight of theta I. Okay. Right. Sorry. Just going back. I'm gonna need this formula to prove that if I have the wedge of two forms, that the weight of the wedge is the sum of the weights. So I know that delta lambda of F1 theta 1 wedge F2 theta 2. So I'm using my left invariant basis now. This is follows from the definition delta lambda F1 theta 1 wedge delta lambda F2 theta 2. We proved that F1 and F2 have weight 0. So this means that this is lambda to the weight of theta 1. Sorry. F1 theta 1 wedge lambda to the W of theta 2 of F2 theta 2. These are coefficients, real coefficients. This is lambda to the W theta 1 plus W to the theta 2 of F1 theta 1 wedge F2 theta 2. So this means that the weight of the wedge is the sum of the weight. And the coefficient doesn't really come into play with the weight. Is this okay? So I have weights of one forms that are easy now that I have the stratification. And then all the other forms, I can recover the weights by taking the sum of the weights of the wedges, right? So now I'm gonna scare you a little bit. So usually when you have your Rham complex, this is what is called a DGA, so a Z-graded differential algebra. What am I saying? I have a grading on the space of forms, and the grading is the degree, right? Here the grading is the degree of the forms. So if I have D, it goes from omega kg to omega k plus 1g. And this is what is referred to as a DGA. Now, the funny thing is that I have two ways to grade weights now. I have the grade with the degree. So I have, yeah, I still have the degree of the form, but I also have the weight. So there is a very quick way. So if you think of the angle group, so I have x1, x2, x3, and x4, and their duals. There is a quick way of distinguishing between a theta 2 and a theta 4 because they have different weights. This is weight 1, this is weight 2, and this is weight 3. In the case without the weight, I wouldn't have a quick and easy way to distinguish between the two because they have the same degree. So I have an extra piece of information. So this is referred to as a bi-graded differential complex. So I have two ways to label the forms, and so I'm going to choose this notation. So it's omega kp. So the first is the degree, and the second one, I'm going to use alpha, and the weight is p. So the first one is the degree, and this one is the weight. So it's just extra information that I have on the forms, okay? And I can use it, and I will use it. And I'm gonna use it in particular to express the action of the exterior derivative. We're ready to look at these things. Oh my God. Okay, so just so it is very good that we have this extra information. Again, it comes from the homogeneous structure. If I'm putting another, so you remember that the angle group had the stratification or the non-stratifiable grading. I can put either. I'm going to have different weights, different properties of the forms, different ways to distinguish them, okay? So it really does depend on so this P, this extra information, depends on the extra structure that you put on. Now we're ready to look at the exterior derivative. So this is the official definition of the exterior derivative. So I start with a K form, and I need to differentiate it. So I need to spit out a K plus 1 form. So I'm going to need K plus 1 vector fields. So D of alpha on x0, x1, blah, 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 xk. This is defined as, so minus 1 to the I xi of alpha evaluated at x0, xi, xk. Bear with me, I'm going to explain in a bit. Plus the sum with I less than j of minus 1 to the I plus j of alpha on the bracket of xi, xj, x0, blah, 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 xi, no, xj, no, or xk. So, right. So this is the definition. Usually what we see in class for differential geometry is this one. So what am I saying? I'm taking alpha evaluated at these k vectors, so x with a hat, I'm removing. So I don't have xi. So I'm going through all of them and I'm removing one after the other. Then I'm going to have a minus, as you would expect. So I am differentiating along xi the function, which is alpha evaluated at these k vector fields. So this is a function, and I'm going to differentiate it along xi, and I do this for each xi that I'm considering. Then what you usually don't see that we're going to heavily rely on is this. Can you see? This one. This is, so notice how this is not differentiating anything. So I'm evaluating alpha on k vector fields. So this is one vector field, and I'm removing two vector fields. So this is -1, -1, +1. So it's still k. So I still have the correct number, but I am evaluating just alpha on vector fields. So this is just a function. I'm not differentiating the function. Right. So first add in pink pink D is the differential part of D, and blue D is the algebraic part of D. Okay. I'm just saying it because I'm gonna use it, and then it's gonna be confusing if I don't explain what I mean by this. So this means that if I'm gonna use another color. So if I differentiate some left invariant form, so as you would expect, pink D is going to be 0. So the differential D is going to be 0 because I have constant coefficients, right? What is not clear is whether the blue is the blue one going to be 0? And in general, the answer is no. Okay. So this is very different from what you would expect. So if you differentiate in R2 plus, if I differentiate dx, this is always going to be 0 because I'm not differentiating. But this is because in R2, I don't have any brackets. In R3, abelian, I don't have any brackets. But in the angle group, for example, I do have brackets. So I'm going to show you how these are not 0. So this is the way you have to compute these things. So I'm going to simplify this, and I'm going to use the action of the algebraic part of D on one forms. So I'm just focusing on that one. So this simplifies to D of alpha. Alpha now is a one form on x0, x1. This is, I know this because if it's just 2, then it's the sign is easy. This is minus alpha on the bracket. So this simplifies quite a bit. And then I can use the Leibniz rule to just compute it for K forms, okay? So I don't need to really use this complicated thing. But this is what I need to construct to study the action of this left invariant thing. So I need to evaluate d alpha, so this 2 form, on the space of on the basis of 2 vectors. So just to make things clear, I have the angle group, and I take x1, x2, x3, and x4 as an orthonormal basis adapted to the stratification, and theta 1, theta 2, theta 3, theta 4 is an orthonormal basis adapted to the stratification for G star. So these are left invariant, by the way. Left invariant, I can start by computing d theta I. So I need, for each one, I need to compute this on the basis of the space of 2 vectors. So this is on x1, x2. I need to compute the action on x1, x3. To compute the action on theta I x1, x4. On x2, x3. On x2, x4, and then on x3, x4. Okay. So I need to compute this. So this is going to be minus theta I on the bracket. So this is non-zero. So this is going to be minus theta I on x3. Then I'm going to do exactly the same for this one. So this is 1, 3. So this is minus theta I on x4. And these ones, so for these ones, it's actually going to be very much simplified. So these are always 0. So I'm never going to get anything that acts like a theta 1 wedge theta 4 as a 2 form. This is the action on this is going to be 0. This is 0, and this is 0 just because the brackets are 0. So then I'm going to have, this means that if I look at d theta 1 and d theta 2, they will act like 0 on all the 2 forms. So these two are the 0, 2 form. Because if I apply theta 1 to x3, it's 0. Now, a different thing is d theta 3. So d theta 3, so this acts like minus theta 1 wedge theta 2 because I have this non-trivial action, but this one is trivial. And then finally, I'm going to have d theta 4, which is minus theta 1 wedge theta 3, because I'm using this non-trivial action. Yeah? Does it make sense for everyone? So basically, it's just linear algebra. So you really have to, this a 2 covector is a linear map, and its action is identified by its action on the element of the basis of the vectors. And so you look at it, and this acts like the 2 form theta 1, theta 2 with a minus. Okay, so d theta 3 will be minus theta 1 wedge theta 2. I'm happy. Okay. Yeah. This one, it doesn't depend on anything. It's you compute them, yeah. Yeah, yeah, yeah. Yeah, yeah. This is the general form. It cannot go, yeah. Okay, so also the fact that if you notice, so the weight of theta 3 is 2, but this is also the weight of theta 1 wedge theta 2, because this is 1 plus 1. This is not a case. So you see the theta 4 has weight 3, which is also the weight of theta 1 wedge theta 3, because it's 1 plus 2. And this is not a case. So if alpha is left invariant, and I'm assuming d alpha is not 0, because otherwise I'm not saying anything, then d of delta lambda of alpha, this is equal to d of lambda to the w, so to the weight of alpha, and I can switch it up. And this coincides. So this comes from the fact that if you're dilating d alpha and applying it to x1, x2, then this is d alpha of delta lambda x1, delta lambda x2. So this is, by definition, minus lambda of delta lambda x1, delta lambda x2. but this is also minus alpha of delta lambda of x1, x2. Okay, so this means that the weight of d alpha, this is exactly the same as the weight of alpha if alpha is a left invariant. What does it mean? It means that the left invariant, so the algebraic part of D, so the blue part, as you would expect, keeps the weight constant. Okay, because it's reading the brackets do have this homogeneous structure. So the D of a constant, so if it's not zero, it keeps the weight constant. So this means that we have all the elements that we need to look at the exterior derivative. So now we're gonna see the full expression of D in terms of weight. So alpha, I take alpha. Alpha, I express this as f function. And theta, it's a left invariant. Ah, I didn't. So omega k p l of g. So it has degree k and weight p. Then let's compute d alpha. So I use the Leibniz rule. So the Leibniz rule to f theta. So this is the same as d f wedge theta plus f d theta. Okay. So I don't mind the algebraic part. Now I know everything about it. So I'm looking at df. df now is a one form. So this is just, I have my orthonormal basis. So this is the sum between 1 and n of x I f theta I wedge theta. Now I'm going to use the extra structure for the stratification. So I'm going to divide this by the step of the stratification. So this, I'm going to take the XLs in VJ of XLF theta L. Now, I'm using this because I don't want to introduce further notation. So what am I saying? For each subspace VJ, I'm going to have the elements of the basis XLs that belong to that, and I'm going to collect them. So this means that this is an element in VJ. I just wrote it. And I collect them all together. But this means that this one form is the dual of an element in VJ. So this has weight J, and this had the weight P. Okay? So this means that each one of these addends has weight J plus P. And I'm gonna call this part of the differential, I'm gonna call this dj because it adds weight J. And as we've seen before, this doesn't add weight. So this I'm gonna call d0. So I have the sum between 1 and s of dj of f theta plus d0 of f theta. So I'm just saying that d alpha is equal to d0 of alpha plus d1 of alpha plus blah, 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 ds of alpha. So this means that the homogeneous structure gives me a way to express d as the sum in terms of the increasing weight. Okay. Now, why would this be ever a problem? This is not a problem if I'm just looking at the homogeneous structure. This becomes a problem with the sub-Riemannian. So in the angle group, I have alpha, which is f1 theta 1 plus f2 theta 2 plus f3 theta 3 plus f4 theta 4. Now, I do the differential. Now, you have to believe me, so I just do the computations. x1, f2 minus x2, f1, theta 1. This is the differential part. I'm just computing it and collecting it. 1 f3 minus 3 f1, 1 3 plus 1 4 minus 4 1, 1 4. I have 3 2 no 2 3 minus 3 2 2 3, and then I have 2 4 minus 4 2 2 4, and then 3 4 minus 4 3 3 4, and then I have the algebraic part that I didn't forget. So this is minus f3 1 2 minus f4 1 3. Now, why is this horrible? Apart from the fact that it's the lengthiest thing I've ever seen. So I'm trying to put this in matrix form. So I'm listing the basis of one covectors and two covectors. So I can do this in matrix form. So this takes the form minus x2, x1 minus f3. Sorry, minus 1, 0. Then I have minus x3, 0, x1 minus 1. I have 1 3 minus x4, 0, 0, x1. I have 0 minus x3, x2, 0. I have 0 minus x4, 0, x2. And then I have 0, 0 minus x4, x3. Okay? So this is what the differential looks like. And it's fine. It's fine. I have the D0 plus the D1 plus the D2 plus the D3. However, if I'm considering the angle group with a sub-Riemannian structure, so V1 now is the admissible directions, what the hell is the order of this? So this has order 2, this has order 3, this has order 2, 3, 3, 2. What are these? What's the order of this? What am I saying? Like what is the principal symbol of this operator? And is the principal symbol injective? Is this going to create, is D star, you've seen adjoint, I believe you do. If I look at this as half of the Hodge Laplacian, is this going to be elliptic, hyperelliptic? This is not the Riemannian Laplacian because the orders are different. So even though I know that, I mean, this should be in Riemannian geometry, this would be elliptic. I'm not sure. I don't know how to treat this. So I can tell you that if you extract, also because, I mean, if you do the D star of that is gonna contain an algebraic part, a differential order 1, 2, 3. So it's a mess. So if you look at the exterior, so if you look at the principal symbol of this, I can tell you it's not injective. So this tells me that it doesn't satisfy the Rockland condition, which is a condition that tells me that I have a hyperelliptic operator. It doesn't tell me that it's not hyperelliptic, but there is virtually no way of me like finding out if this is hyperelliptic. Okay? So this is one of the many problems that arise, okay, when I'm considering sub-Riemannian stratifiable groups, okay? So I'm saying this because the fact that this differential can be expressed as the sum of these things is not linked to the sub-Riemannian structure. This is linked to the homogeneous structure. But having a sub-Riemannian structure that is compatible with the homogeneous one tells me that the increasing weight coincides with the differential order. So D0 was the algebraic part. I'm not differentiating. D1, increasing weight 1, differential order 1. D2, differential order 2. D3, different. So it's a nice way to encode the behavior, okay? So this is where the problems start to appear clearly, okay? So it is also done, if you're familiar with anything sub-Riemannian, if you look at the sub-Laplacian, you're not considering the whole Laplacian of functions, because then you would get differential orders that are higher, that you don't know how to treat, basically. So so this is just a hint if you're already familiar, but basically this is where problems start to arise. So the thing is, I would like, everyone would like to have an elliptic Hodge Laplacian on forms, right? You can do a lot of nice things, but the problem is that if you put a sub-Riemannian structure, this cannot be done using the differential coming from the Rham complex, because these problems start to arise, okay? Then there are an infinite amount of problems that arise using the Rham complex, but this is like the most clear way of, like, yeah, the quickest way of finding a problem. And I think, yes, I'm done. Thank you.
Other questions there?
Yes.
Thank you. The Rockland condition is not known if it also for this kind of operator, or it simply does not work.
It doesn't work.
Okay.
It doesn't satisfy the Rockland condition. I mean, the Rockland condition is stated originally for scalar operator. This is a matrix valued operator. So you have to translate it, but it doesn't.
So, but this is a sufficient condition. So that's the point.
So it is the quickest and easiest way to say that the operator is hyperelliptic. So
yeah,
to be completely honest, we don't know if this operator is hyperelliptic.
An open question.
I don't think it is, but I mean, it's a mess.
Thank you.
Other questions? Okay. If not, let's thank Francesca again.
Thank you.
Okay. Oh, okay.
Okay. So, yeah, we can start with Robert's second lecture. Please.
Okay. So, sorry, is this too loud? Okay.
this, I see. Okay. Okay, so last time we talked about a coarse version of the Lebesgue differentiability theorem. Last time we talked about the following result, that if f is a function from R to R, which is Lipschitz, and if we define d epsilon is a set of points xr such that f is close to an affine function. Sorry, f is not close to an affine function. F is not epsilon differentiable on the interval from x minus r to x plus r, then this set is small. Then for all epsilon greater than 0, d epsilon is what's called Carlson, which is to say that the integral from 0 to s of the integral from y minus s to y plus s of the characteristic function of d epsilon with respect to dx dr over r is bounded by a constant s times, is bounded by s times a constant depending on epsilon. And the idea of this is that what this means is that d epsilon is small, that at most points and most intervals around those points, f is close to an affine function. F is epsilon close to an affine function. And so I just want I wanted to start today by saying two things about this theorem. So one, this came up as a question at the end of last lecture. This does not imply Lebesgue. It doesn't imply the traditional Lebesgue, because just because a function is epsilon close to a to an affine function at many different scales, that affine function doesn't have to be the same affine function. This implies that for almost every x, there exist for almost every x, the fact that this set is Carlson means that the set of R such that XR is in this set is relatively sparse. So for every x, there exist infinitely many smaller and smaller scales where the function is epsilon differentiable in the interval from x minus r to x plus r. And if we take epsilon going to 0, we can construct a sequence of lengths, R1, R2, so on and so forth, such that f is 1 over n differentiable on the interval from x minus Rn to x plus Rn, and the Rn go to 0. The difficulty is that this only tells you that can you see if I write down on the bottom of the board, or do I need to stop? Okay. But this only tells you that it's close to affine on all these different scales. It may very well be that, at one scale it is epsilon close, or epsilon Rn close to one affine function, and then at a smaller scale it's close to a different affine function, and then a smaller scale it's close to another affine function, and so on and so forth. So that, in different terminology, that if there is a tangent cone, it has to be a line, but you don't know that there exists a unique tangent cone. Your function may look different at different scales. And so there are ways to fix this. You can use these same methods to show, if you try to construct a function like this, You know, if you try to construct a function that does, you know, go one direction at one scale, and then another direction at another scale, and then another direction at a smaller scale, and so on and so forth, what you end up with, if you do the most natural construction, is you end up with a function like this that looks different at different scales, but the points where this happens are rare. Like if I construct a function like this, it is really bad at this point, but anywhere else you can find, you know, a unique tangent cone. And so what you need in order to fix this, what you need in order to prove Lebesgue using these methods, is basically a way to show exactly that. To say that if you have a function which is, you know, close to an affine function at one scale, then in a certain sense, at most smaller scales, it's close to the same affine function. That if you have a lot of smaller scales where it's close to a different affine function, you know, if it's close to, you know, this other, if it's close to this slope, you know, here and here and here and here and here and all over throughout this, then just like lack of epsilon differentiability, that's going to contribute to the length of the curve. That's going to result in a curve that has to look something like, you know, has to go like that and like that and like that and like that. And if you do some work, you can show that that also contributes to the length, and you can use that to say that this doesn't happen very often. But that's more difficult. That's more, you know, at that point, the advantages of this method, the nice geometric intuition starts to become a little bit diluted. So yeah, so this doesn't quite imply Lebesgue. And the other point I wanted to talk about, that's quite heavy. The other point I wanted to talk about is that this, you can generalize this to other spaces. So especially if you say f is a function from R to X, where X is a Banach space. Can we prove this same sort of differentiability? Well, it depends on X. So just like before, we could just like before. We can try to define the same thing. So we can let L sub k of an interval be the length that you get by approximating f on that interval by a sequence of 2 to the k segments. So this is the sum from, let's say, I equals 0 to 2 to the k minus 1 of what? Distance in x between f of, and say our interval is the interval from A to B, just a fixed notation, A plus 2 to the k times B minus A minus f of A plus I over 2 to the k times the length of the interval, right? This is the same as before. We're taking our curve, and then we're breaking it up into dyadic segments, k times, and then we're taking the length of that piecewise linear approximation. So we can define this just like before. We can define gamma of I to be L di minus L naught I. This defect here, the difference in length between the two endpoints and this piecewise linear curve. And then just like before, a lot of the same sums and integrals we did last time still work. If we define gamma I like this, then, you know, the set of x and r such that gamma of, oops, I need to normalize this. This is divided by the length of I. Then just like before, the set of x and r such that gamma is large, so gamma of x minus r to x plus r is greater than delta, is Carlson. But the difficulty of changing to a different space is that this might no longer imply close to that f is close to linear. If x is uniformly convex, for example, x is an LP space with p strictly greater than 1, strictly less than infinity. Then you do then you do get a version of this theorem, because in that case, gamma of I small implies that f of I is close to a line. Exactly how close depends on the target space, depends on x. But for instance, you can show that if x is an LP space, with p, let's say greater than 2, less than infinity, then you can show, for instance, that if I take a line segment in an LP space of length L and I perturb it by epsilon L, you don't quite have the same Pythagorean theorem as L2 because it's not a Hilbert space, but you can show that the length, let's call it L prime, of the perturbed curve is at least, what is it? I think it's 1 plus a constant times epsilon to the p times L. And so in particular, if gamma is sufficiently small, if these approximations are not too much longer than the original line, then these approximations have to be close to the original line, and so you can prove this same sort of differentiability. You can prove that maps to a uniformly convex Banach space still satisfy this same property. The difficulty is in the case when you don't have a uniformly convex Banach space. In that case, you can't, or you may not be able to. In that case, well, so for example, if I take x to be L1, let's say L1 functions on the interval, then we can define f of t to be the characteristic function of the interval from 0 to t. You can check that f is a geodesic in the sense that the distance between f of s and f of t is equal to the difference between s minus t. So this is an isometric embedding of the interval into L1, but f is not epsilon differentiable anywhere, right? If it were epsilon differentiable, you would expect that if you take 2 points s and t, then f of s plus t over 2, f of the average, should be close to the midpoint of f of s and f of t. But it's easy to check that if I have f of s is the characteristic function of 0 to s, f of t is the characteristic function of 0 to t. Their average is some function that looks like this. Oops. The average is a function that looks like this, but the midpoint of f of s and f of t is a function that looks like this. They're always going to be a certain distance apart. So f is not epsilon differentiable almost everywhere, and part of the reason why is because this doesn't work. You can have 2 points f of s and f of t where there are many different geodesics from s to t. Oh, yeah, you can even see this in L1 of the plane. There are many different geodesics from S to T that all have the same length. And so you no longer get any coercivity from the length. If I have a curve which is only slightly longer than the distance between those 2 points, that curve could be any of a number of curves. So, it's okay so far? So today, my main goal today is to try to talk, is to try to talk about generalizing this coarse version of Lebesgue to other spaces. And so the model is, well, what's the first generalization, or what's one of the first generalizations of Lebesgue's theorem is Rademacher's theorem. So Rademacher tells us that if f from Rm to Rn is Lipschitz, then f is differentiable almost everywhere. If we want to quantify this, what can we say? Well, a quantitative version of this should look similar to our quantitative Lebesgue. If f from Rm to Rn is 1 Lipschitz, then f should be epsilon differentiable on most balls again. Which is to say, so let's define, so let's say that f is epsilon differentiable on a ball of radius r around x, if there exists some affine function alpha such that f of y minus alpha of y is less than epsilon r for all y in the ball of radius r around x. And then we can define what it means for f to be epsilon differentiable on most balls, essentially the same way as before. So specifically, we can define a set just like before, d epsilon is a set of xr such that f is not epsilon differentiable on the ball of radius r around x. Then we claim that for all epsilon greater than 0, this set is Carlson, in the sense that essentially the same thing, except we replace the intervals with balls. So we still integrate from, so for all y in the domain, all s greater than 0, if we set up a double integral where we integrate over the radius of the ball, and we integrate over the ball of radius r around, the ball of radius s around y, the characteristic function of d epsilon at x in the ball around y, radius r, where we integrate x over the ball around y, and r varies from 0 to s to measure dr over r. So again, what we want to say is that on average, if we pick a point, then the set of radii where xr is in d epsilon, that ought to be small on average. And so we want this integral. Well, this integral is essentially taking the average of that quantity, the average of the number of bad scales at different points x in the ball around y. And so we want this integral to be bounded by some constant depending on epsilon. And since we're integrating over the ball of radius S, we have a factor of the size of the ball of radius S. Right, so this is what we mean for a set to be Carlson. For a set, and previously we had this for a set in R cross R, and now we have this for a set in Rm cross R. This is what we mean for a set to be Carlson, and we want to say that the set of balls where F is not epsilon differentiable on that ball corresponds to a Carlson set. Is this okay so far? Okay. So, like I said, the basic idea here is the same as before. We can think about this as, you know, d epsilon consists of the set of balls where our function is sort of bad, and we can think about this double integral as, well, we're looking at balls centered in the ball of radius S around Y, where the radius is between 0 and S. Again, this roughly corresponds to saying that F is epsilon differentiable on most subballs of any ball BYS. Okay. So how do you prove this? Strategy basically goes in two parts. One, we want to use the one-dimensional case. We want to claim that for most balls in the domain, F is close to linear, is epsilon differentiable on most of the lines through B. This is going to use the coarse version of Lebesgue that we proved last time. And then two, once we know that, the set of balls where this happens, the set of balls where F is epsilon differentiable on most of the lines through those balls, that ought to be our set where our function is epsilon differentiable on the whole ball. So we want to show that if F satisfies this, if F is, say, delta differentiable on most of the lines through some ball, then it's epsilon differentiable on the ball itself, on the whole ball. Okay? Okay. So let's do this. So for the first part, we want to apply the one-dimensional case. So specifically, what we're going to do is we're going to foliate Rm by parallel lines and then apply the one-dimensional case to each of those lines. So let's let V, for any V in the unit sphere. So this is going to be the unit sphere. We're going to define d epsilon V. Basically, this is going to be epsilon differentiability in a particular direction, in the direction of V. So we're going to define d epsilon V to be the set of points x and r, such that F is epsilon differentiable close to an affine function on the line segment between, let's say, so we want to be in the direction of V on a line segment of length R. So this is going to be the line segment from X minus RV to X plus RV. Then the lines in the direction of V foliate Rm. We can cover Rm by lines in the direction of V. And the restriction of f to any one of these lines is a one-Lipschitz function. So the restriction to any of these lines is a one-Lipschitz function, so we can apply the one-dimensional version of the theorem to those one-Lipschitz functions. And that tells us that for most intervals on those lines, f is, oops, oh, sorry, I need this to be not epsilon differentiable. The one-dimensional version tells us that on most of the intervals in these lines, the function is epsilon differentiable, and so this set ought to be small. And it's not too hard to calculate that this set is in fact Carlson. For all epsilon, for all V. So what does this tell us? This tells us that f is differentiable, is epsilon differentiable on most line segments. That's not quite what we want here. Here we want to say that we can find a lot of balls so that on each one of those balls, f is differentiable on most of the line segments through the ball. That's not quite what we have here. This tells us that for most line segments, f is epsilon differentiable on those line segments, but there could still be some balls that are particularly good or particularly bad. And the example I want to think about is, say, if I have, f of x is norm x, so the graph is a cone, then you have some points that are good and some points that are bad. If I take, say, the origin, then there's a lot of curvature. The function has a lot of curvature near the origin. There are a lot of lines through the origin where the function is not very differentiable, where the function is not close to a line. On the other hand, if I take a point that's a little bit away from the origin, well, this is a round cone. This is a cone shape. If I take a ball that's close to the origin but not too close, then, well, the surface, the graph is made up of a bunch of lines going out from the vertex of the cone. Our function is affine along those lines. It's a little less affine if we try to go around the cone. It's got a little less affine if we try to go in the circumferential direction. So, if I take a ball like this, then it's close to affine on some curves, not necessarily all curves. But if I extend this out further and further, the curvature of the cone gets flatter and flatter as you go further away from the origin. And so if we take a ball that's either, far away from the origin, or by scale invariance, if we take a ball that's close to the origin but very small, then now the curvature is lower. There are more lines where this function is affine, or more lines where this function is close to affine. It's okay? So we want to go from saying that our function is affine on most lines to saying that on most balls our function is affine on most lines. Oops, wrong side. Okay. So let's define a corresponding set. Let's let T delta be the set. This is going to correspond to the set of balls where a delta proportion of the lines through those balls are bad. Where this is going to correspond to the set of X and R such that, what do I want to say? Integral over all directions, integral over all points in BRX. of characteristic function of d delta v, evaluated at the point, what do I got here? I guess y, let's say 2r, so that we have enough length here, with respect to dx dr over r. So what is this? So we're integrating over all, sorry, not dr over r, dx dv. Let's say d nu v, where nu is the uniform measure on the sphere. And that should be m minus 1. So what are we doing here? Oh, shoot, I need a condition there, and I'm out of space. Where this integral is bigger than delta times the measure of the ball. So this is our set. So what is this? So the idea here is that we're integrating over the unit sphere and the ball. So essentially what we're doing is we're picking a random point in the ball, and then we're picking a random direction in the unit sphere at that point. And we're looking at the line that stretches out from y to y plus 2rv to y minus 2rv. And we're asking, is our function delta differentiable on that line? And so in particular, this set corresponds to the points, this set corresponds to the balls where there are a lot of lines, at least a delta fraction of lines, where the function fails to be delta differentiable. This set corresponds to oops. It's straightforward to say that if you have a point which is not bad, if you have a point which is not delta bad, then the probability that a random line segment of length, I guess I'm going out 2r in one direction, 2r in the other direction, so random line segment of length 4r fails to be delta differentiable is less than some constant times delta. So if delta is small, then 99% of the line segments through the ball, a random phase through the ball. So this is the set of points where there is a so T delta is the set of points where there is a non-negligible probability that a random line segment through the corresponding ball fails to be delta differentiable. Conversely, the set of points that are not in T delta are particularly nice. Most of the line segments through those points are epsilon or delta differentiable. And it is not too hard to show that this is also Carlson. You can find some of the details. So you can see the notes on my website for some of the details. But It's not too hard to show. The main trick is basically a convolution trick. I mean, the idea of this is that you have some. The idea of this is that if you have some set in the plane with some density, if you have some set in the plane with some density, you want to claim that the set of balls where the density of that set inside the ball is large is bounded. You want to bound the local density by some sort of measure of the set. And there are nice convolution arguments to do that. What you can do, for instance, you can take if E is a subset of Rm, then we can look at the convolution of the characteristic function of E with the characteristic function of the ball of radius r. And this is a function, so the value of x tells us the measure of E intersect the ball of radius by radius r around x. And so if we want to bound the number of x where this is large, that's not too hard to do. Then the set, how do I want to do this? I want to do this with more space. Then you can check if you want. Then if you want to bound the set of x such that this is large, let's say this is at least a delta fraction of the ball, then you can do that essentially using Chebyshev. The measure of this set times delta measure of the ball is less than or equal to the L1 norm of this function. Sorry, I'm running out of space there, so that's the L1 norm. And that L1 norm is easy to bound. And this is a convolution, so that L1 norm is just the L1 norm of the pieces of the convolution is norm E times norm of the ball. And so the measure of this set, call the measure of this set, well, let's call this set, E delta, the set of balls where E has density at least delta. Then what we end up with is that the norm of BR, the measure of E delta is bounded by the measure of E times the measure of the ball. We can cancel this out and conclude that the measure of E delta is no more than delta times bigger than the measure of E. And so in particular, oops, I've lost it. In particular, if we have a bound on the size of these sets, which we have from the Carlson condition, then we have a bound on the size of these sets, which is no more than about delta times bigger. Is it okay so far? So that's the first part of what we need, is that this set where this set of delta bad balls is also Carlson. The second part is to use that property. The second part is to show if I have a point, if delta is sufficiently small, and if I have some point xr, which is not in T delta, I want to show that then f is epsilon differentiable on that ball. Right? And there are two ways we can do this. Well, I mean, there are more than two ways to do this, but there are two ways that I want to show you. And the reason I want to show you two ways is because one of them is a nice, quick trick that can save you, a few pages in a paper, and the other one is going to be easier to generalize. So let me start with the quick trick. One, we can prove this using compactness. And here's how we do this. Suppose not. Suppose that this is not true. What does that mean? That means that there's no delta, so that if xr is not in T delta, then f is epsilon differentiable on Brx. What that means is that there exists functions, let's call them f sub n. Let's not call them f sub n because I already used n, f sub I from Rm to Rn. Such that we can find points xi, ri, which are not in T 1 over I, which are not in T of 1 over I, but f sub I is not epsilon differentiable on the ball of radius ri around xi. All our notions are scale invariant and translation invariant. So instead of taking the ball of radius ri around xi, we may as well rescale. We may as well rescale and translate so that xi is the 0 vector and ri is 1. And so all this holds for the unit ball. Then these are all one Lipschitz functions on the unit ball, which are delta differentiable, or which are 1 over I differentiable on an increasing fraction of the lines through the unit ball. By Arzela-Ascoli, we can pass to a subsequence such that f sub I converges to some function f uniformly on compact sets. But if this converges uniformly on compact sets, in particular, it converges uniformly on all of these lines through the unit ball that we're concerned about. And so in particular, this implies that f is in T 1 over I for all I, which means, well, if f is in T 1 over I for all I, this means that f is epsilon differentiable. Better than that, f is affine on every line segment through B. But if you have a function which is affine on every line segment through the unit ball, it's not too hard to show that that means that it's actually affine on the unit ball. So F is affine on unit ball, but, oh yes, sorry. Thank you. But yeah, so then the limit is affine on every line segment through the ball. You can check that if a function is affine on every line segment through the ball, then it's actually affine. But these FIs are supposed to converge uniformly to F. These FIs are supposed to converge uniformly to F. So the FIs are epsilon differentiable when I is large. And that's a contradiction. We said that they were not epsilon differentiable. And so we can do a quick compactness argument to say that if we have a sequence of functions that are getting better and better on larger and larger percentages of the lines, then those functions have to converge to an affine function. And if you have a sequence of functions that converges to an affine function, then eventually they have to be epsilon close to an affine function. So this is one argument. This is very nice. It's a little bit hard to generalize. Because you need this specific result, that if you have a function that's affine on every line segment, then it's actually affine on the whole ball, and that can be a little bit tricky to generalize to other spaces. So let me present a slightly more technical, but a little bit easier to generalize argument, which we'll call argument 2. So, sorry, before I do this, are there any questions about anything so far? Yeah? Uh-huh. Uh-huh. Yeah. Oh, shoot. Sorry. I guess I really should have. Yeah, I guess I should. Yeah, so I guess I should have added a subscript to the to T to say, this is applying it to Fi, and so if I want to be so in that notation, I want to say that the vector 0, 1 is not in TF 1 over I for all I. Yeah, sorry. More questions? Okay. Okay. So the other way we can do this is we can use parallel lines. Basically, it's not too hard to check that for all epsilon greater than 0, there exists a delta such that if xr is not in T delta, then f is, let's say, epsilon square differentiable on every, not just most, but in fact every line segment x minus r, or y minus rv, minus 2rv, y plus 2rv. The reasoning is that if not, if f is not, let's say, 2 epsilon square differentiable on some line segment L, then because f is 1 Lipschitz, if it's not differentiable, if it's not close to affine on some line segment L, then if we take any nearby line segment, any sufficiently close line segment L prime, and there's a positive measure of nearby line segments, then it's likewise not epsilon square differentiable on nearby L prime. And so if you can find one, so if f is, or sorry, if xr is not in T delta, then that means the set of bad line segments through the ball of radius r around x is less than a delta fraction of the set of lines. So if delta is sufficiently small, then, well, sorry, let me say it the other way around. Yeah, so if f is, if there's some line segment where f is not epsilon square differentiable on that line segment, then it's not epsilon square differentiable on these nearby line segments either. And so in particular, there's some positive measure of line segments where it fails to be epsilon square differentiable. And so in particular, xr would have to lie in T delta when delta is sufficiently small. So if we choose delta sufficiently small and ask that xr is not in that T delta, then you can use the Lipschitz condition to say that it's not just epsilon square differentiable on most lines, it's in fact epsilon square differentiable on every line through the ball. Once we know that, well, the trouble is we know that on every line through the ball, our function is close to an affine function. What we don't know is if I take two different lines, what's the relationship between the corresponding affine functions? But if we have two parallel lines, then we can use the Lipschitz condition to relate those two affine functions. So let me define, what do I want to do? Yeah, so let me define for a direction v and a point y in the ball, we'll define a sort of course derivative. So the course derivative in the direction of v, f of y, to be just the difference quotient at one particular length. So this is going to be f of y plus rv minus f of y minus rv over the distance between those is 2r because v is a unit vector. Right. So this is just the you know, it's the slope of the line segment connecting the two endpoints. So then if I have two nearby points, actually, I guess I want to say two things. Then on one hand, by this epsilon square differentiability, for every y in the ball and for every t which is not too big, norm t less than r, we can use this course derivative to approximate the function. F of y plus t times v is f of y plus f of, plus t times this course derivative plus an error term where the error term comes from the epsilon squared differentiability. So that error term is on the order of epsilon squared times the radius of the ball. So that's one thing. For another thing, if I have 2 points y1 and y2 in the ball, then the difference between these course derivatives is bounded in terms of the Lipschitz property. The difference between these two derivatives, what is this? Well, that's each of these comes from this difference quotient. So I can rewrite this. This is less than or equal to the difference between f of y1 plus t plus rv minus f of y2 plus rv over 2r plus the difference between f of y1 minus rv and f of y2 minus rv over 2r. But the distance between y1 plus rv and y2 plus rv is the distance between y1 and y2. Likewise, the distance between these two is the distance between y1 and y2. And so this whole thing is less than or equal to the distance between y1 and y2 over r. So this coarse derivative changes slowly. In particular, if y1 and y2 are both in a smaller ball, then the difference between these coarse derivatives is less than a constant times, these are epsilon r apart, so epsilon r over r is less than a constant times epsilon. And so we can approximate our function on the small ball just in terms of the derivatives at the center. So in particular, this coarse derivative is close to the coarse derivative at the center of the ball for all y in the ball of radius epsilon r around x. And so let's use the coarse derivatives at x to define a coarse gradient. Let's define so I'm just going to say the coarse gradient of f at x is the vector you get by taking the partial in the direction of E1 up to the partial in the direction of EM. Oops. Where the E1 up to EM is a standard basis. And then for all y in the small ball, we have that f of y is f of x plus y minus x dotted with this coarse gradient plus an error term. How big is this error term? Well, what are we doing? What are we doing here? We're saying that we can take here's our ball, here's our center, here's our point y. Say here's our point y. What are we doing? We are applying this coarse gradient estimate in this direction, and then in this direction, and then in all the other directions that when m is greater than 2, you have more directions. And so how much error do you pick up? Well, every time you apply this approximation, you pick up this epsilon square r error coming from the epsilon square differentiability. We do that a couple of times. But also, we're not applying exactly this approximation because we're dotting with the coarse gradient at the center. So we also pick up an error term because the coarse gradient here, the coarse gradient along this line, is different from the coarse gradient along this line. But because these are epsilon r apart, the difference in the course gradients is order epsilon. And so we pick up two sources of error. One, we apply this estimate m times, so we have an error like m times epsilon square r. And we pick up another source of error, which is that our course gradients are different here and here. We pick up that error, again, m times. How big is that error? Well, our course gradient changes by about epsilon, and we are moving in direction epsilon r. We are moving a distance epsilon r at each step, and so that's an error of epsilon times epsilon r. It's also m epsilon square r. And so what do we have? That says that f is m epsilon r square r close to an affine function on the ball of radius epsilon r. So f is order of epsilon square r over epsilon r is order epsilon differentiable on the ball of radius epsilon r around x. And that's what we want. That tells us that for most balls, it's not exactly the way we stated it before, and technically this tells us that for most balls, we can pass to a smaller ball on which f is very close to affine, but it's that change in radius doesn't affect the Carlson condition. The set of balls where this is epsilon differentiable is still Carlson. Is this okay so far? Okay. So yeah, so we can go from the one-dimensional case to the higher dimensional case because we have all these parallel lines, because we can take Rm and we can decompose it into foliations by parallel lines going in different directions. You can do the same thing for a lot of metric spaces, it turns out. So a lot of this was done. So I guess the main the results in this direction are due to Plateau, who proved differentiability for maps between Carnot groups, between sub-Riemannian manifolds. These are some of the nilpotent groups that Francesca was talking about. The results due to Cheeger, who proved differentiability for maps from X to R when X is what he called a PI space. You can define what a PI space is. It's defined in terms of it's a space that satisfies a particular inequality, which is based on the Poincare inequality. That's the term PI space. But part of what that inequality means is that it's a space that has a lot of geodesics. And so you can prove differentiability for spaces that satisfy this property. What I want to do in the time I have left. So how much time do I have left? 20 minutes? Okay. So what I want to do in the time I have left is talk about how this works for Carnot groups, talk about how this works for Plateau's theorem, because we can generalize this parallel lines argument to Carnot groups pretty nicely. So just to recall what we're talking about, just to recall what I want to talk about here. So the way that I usually think about this is in terms of geometric group theory. So the idea of geometric group theory is that you want to study a group in terms of the geometry of its Cayley graph. And so in particular, the simplest example of Plateau's theorem is in the case where your group is the Heisenberg group. And so there are a couple ways you can define this. You can define this either in terms of, you can define the Heisenberg group either in terms of upper triangular matrices. You can define this, Francesca talked about how to define nilpotent Lie groups in terms of their Lie algebras. The Lie algebra of the Heisenberg group is the Lie algebra generated by, call them capital X, capital Y, capital Z, such that the bracket of X and Y is equal to Z, and the bracket of X and Z is equal to the bracket of X of Y and Z is equal to 0. You can define this in terms of a multiplication. This is the same Baker-Campbell-Hausdorff setup that Francesca discussed. In this case, because the bracket is pretty simple, there aren't that many terms in the Baker-Campbell-Hausdorff formula. You can write the multiplication, you can write the group as R3 equipped with the multiplication x, y, z times x prime, y prime, z prime is equal to, and this is the same as the formulas that Francesca was using for the angle group, x plus x prime, y plus y prime, z plus z prime, plus a term coming from this one non-trivial bracket, which is x y prime minus y x prime over 2. Right? So this, like I said, geometric group theory is about studying the geometry of a group, or by studying the geometry of the Cayley graph of a group. This group has a lattice, is generated, which is called the integer Heisenberg group, is generated by, well, you know, there are lots of ways to do that. Let's use this multiplication, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And so the Cayley graph is going to consist of the elements of this lattice where you have an edge between two vertices, if you can go from one to the other by multiplying by one of the generators. And so what does it look like to multiply by one of these generators? Well, x, y, z times 1, 0, 0 is, what do we do? So x plus 1, y, z plus, we have a term coming from there, which is xy prime over 2, so x over 2. If we multiply x, y, z times 0, 1, 0, we get x, y plus 1, z minus, oh shoot, did I do that wrong? No, sorry. Multiplying by x, so minus y over 2 plus x over 2, right? And if we multiply x, y, z times 0, 0, 1, we just get x, y, z plus 1. So the Cayley graph, okay, I'm going to try to draw this. The Cayley graph, what does this look like? Well, so if we start at the origin, if we multiply by x any number of times, that's just because the y coordinate is 0, that's just going to go along the x-axis. If we multiply by y any number of times, that's just going to go along the y-axis. And if we multiply by z, that's going to go along the z-axis. But if we get further out from the origin, then, well, what happens? If the x-coordinate increases, then multiplying by y increases the y-coordinate by 1, and it also adds x over 2 to the z-coordinate. So if we go further, if we go out along this axis, then these cosets of then the groups that we get, then multiplying by y starts to take us upward in the z direction. So we can think of this in terms of lines that tilt upward as you go to the right, that tilt downward. This is, sorry, that tilt downward as you go to the left. Sorry, the perspective is kind of weird, but think about it. It's going down. Yeah. Sorry, the perspective is just going to be kind of weird. So if you multiply by y, that corresponds to going along lines where the slope of the line depends on the x-coordinate. Same thing if you multiply by x. If you multiply by x, then likewise, the slope of the line that you get by multiplying by x depends on the y-coordinate. When the y-coordinate is large, it tilts one way. When the y-coordinate is small, it tilts the other way. So let's say this is the positive y direction. So as we go in the positive y direction, these lines are going to tilt down. As we go in the negative y direction, these lines are going to start to tilt up. In particular, the notable thing about the geometry here is that if we start at the origin and we go n steps in the x direction, and then we go n steps in the y direction, and then we go n steps back in the x direction, n steps back in the y direction, you can do the multiplications, or you can look at the geometry. Either way, what you see is that this is x, y, z plus n squared. Basically, because if you go n steps out in the x direction and then n steps in the y direction, it's tilting upward, so you end up with a much larger z coordinate. And then same thing here. Now we're somewhere out here with positive y coordinate. And if we go in the negative x direction, it's going to tilt upward again. And then we're going to go back to the origin. So we end up tracing out a path that looks like, we go out, we go up further, we go back. We end up n squared steps above where we started. It's okay so far? And so you can calculate distances. You can calculate distances in this metric in particular, the distance between xyz and xyz prime is on the order of square root of difference. Basically, because if z and z prime are very different, if you have 2 points that are very far apart in the vertical direction, then there is a nice path like this that goes out and around and up. It goes around in a spiral that takes you from this point to this point, and the length is like the square root of the vertical distance between those 2 points. Is it okay so far? So, 10 minutes, okay. So Ponceau proved that any Lipschitz map well, he proved a much more general theorem than this, but I'm just going to state the simplest case. So F from the Heisenberg group to R is what's called Ponceau differentiable. I don't think he didn't call it this. He didn't name it after himself, but subsequent mathematicians named it after him. Is Ponceau differentiable almost everywhere, which is to say that for almost every, let's call it G in Heisenberg group, there exists a homeomorphism, let's call it alpha sub G from Heisenberg group to R, such that there exists a homeomorphism from the Heisenberg group to R, such that this homeomorphism infinitesimally approximates F near X. So what do I want to say? I want to say that the distance between F of Y, I guess the image of F is in R, so I can say that the difference between f of h and f of g is the is alpha sub g of the difference between h and g is g inverse h, plus an error term where that error term goes to 0 with the distance between g and h. Do I have that right? Yeah. So our function homomorphism, like oh sorry, I said homeomorphism, a homomorphism. Right. So the idea is the same as differentiability from Rm to Rn. Differentiability from Rm to Rn is when a function can be approximated by an affine function. Here, because we have a group structure, we replace the affine function with a homomorphism. We ask that our function can be infinitesimally approximated by a homomorphism. And just like Rademacher's theorem, we can do this coarsely as well. You can say that you can define epsilon Ponceau differentiable. You say that f is epsilon Ponceau differentiable on a ball if there exists some homomorphism such that the distance between f of y and what do I want to say, f of x alpha of f of y minus f of x is approximated by alpha x, alpha of x inverse y. This difference is less than or equal to epsilon times r for all y in Brx. Same as before, we're approximating our function by this homomorphism up to an error epsilon r. Then a Lipschitz f from h to r is epsilon Ponceau differentiable on most balls, where again, we can define that we can make this idea of most balls rigorous in terms of a Carlson condition. And so how does this work? Well, it works essentially the same as Rm. So just like for Rm, we can break it up into two parts. First, well, just like Rm, the Heisenberg group is foliated by a bunch of parallel lines. In this case, these are the parallel lines in the x direction. These lines, these lines that I just erased, where they tilt upward. Sorry, this is where they tilt upward as the y coordinate increases, and the lines in the y direction where they tilt upward and downward as the x coordinate changes. Heisenberg group is foliated by lines by exactly the same arguments that we made before on most balls. F is epsilon differentiable on most of the lines through these balls. And then two, we want to say that if F is epsilon differentiable, let's say delta differentiable on most lines through B, then F is epsilon differentiable on B. And again, there are two ways to do this. You can do this by compactness, but now it's a little bit trickier to say that if you have a function which is affine on every one of these lines and every one of these horizontal lines through a ball, then it's in fact affine on the whole ball. And in fact, if we replace the Heisenberg group by other Carnot groups, it's not true anymore. There are Carnot groups where there are functions that are affine on every line, every horizontal line, but not affine globally. Or you can apply parallel lines. Specifically, if I take two lines like this, if I take 2 points G1 and G2, and I look at the line through G1 and the line through G2 in the x direction, it's not too hard to show that the distance between G1 times, let's say, R00 0, and G2 times R00 0, it's not too hard to do a calculation and show that this is bounded by the square root of the distance from G1 to G2 times R. So it's not quite as parallel as in Euclidean space. In Euclidean space, if you have two parallel lines starting at G1 and G2, then anywhere you go, the distance between them is the distance between G1 and G2. In the Heisenberg group, you start at 2 points G1 and G2. If the further out you go, this distance grows like root of the distance times R. But so it's not quite as parallel as in Euclidean space. This isn't constant, but it grows relatively slowly with R. It grows sublinearly with R. And so in particular, when we do this same argument, we can define the course derivative in the x direction, the course derivative in the y direction, the same way as before. And if the distance between G1 and G2 is less than epsilon r, then the difference in their course derivatives, course derivative in the x direction minus the course derivative at G2, ends up being bounded by, well, now we have a couple of difference quotients with root epsilon r squared on the top and r on the bottom up to a constant. And this is just root epsilon. So and this lets us argue as before. This lets us say that if I have a point x, if I have a point G, where the where f is delta differentiable on most of the lines through the ball around G, then just like before, the Lipschitz condition lets us conclude that it's in fact delta differentiable on every line through the ball. And then this condition on parallel lines tells us that if we pass to a smaller ball, those course derivatives are nearly constant on that smaller ball, and therefore we can use Taylor expansion on that smaller ball to say that f is epsilon differentiable, if epsilon Poincare differentiable on sufficiently small balls. Right? In particular, this implies a theorem of Poincare and Sem's, which is that if we take this Cayley graph, I'll let gamma be the Cayley graph of the Heisenberg group, of the integer lattice in the Heisenberg group, there is no bi-Lipschitz map embedding from this lattice to Rk for any k. The proof is that f is epsilon Poincare differentiable on most balls. In this case, because this is a discrete object, because this is a graph, when we say most balls, we're talking about very large balls. So I can find some very large ball on which this function is epsilon Poincare differentiable, which means that it's approximated by a homomorphism on that ball up to an error of order epsilon. But the thing about the Heisenberg group is that because it is non-abelian, any homomorphism from the Heisenberg group to R has to kill its commutator subgroup. The commutator subgroup, the z-axis, is in the kernel of that homomorphism, and so that commutator subgroup gets collapsed to a point by the homomorphism. So if you find this ball where our function is epsilon Poincare differentiable, then you can take 2 points along the z-axis of that ball. You know that the homomorphism maps those to the same point. There's an epsilon error introduced by f because it's not exactly equal to the homomorphism, but you're still taking 2 points that are about r apart and sending them to 2 points that are about epsilon r apart, and that breaks the bi-Lipschitz condition. And so you can use this this coarse Poincare to prove Poincare sense. This result from geometric group theory that the Heisenberg group does not bi-Lipschitz embed in any Rn. Yeah, and that's where I want to stop today.
So, questions?
Thank you. Do you expect this theorem also to be generalized to more general groups, this rigidity theorem?
Well, yes. Yeah, so I've stated everything for Heisenberg, but you can do the same thing for arbitrary nilpotent groups. Because if you have an arbitrary nilpotent group, you can take a generating set, and then you can take a foliation corresponding to those one-parameter subgroups, and apply the same arguments. These one-parameter subgroups or these cosets of the one-parameter subgroups give you these parallel lines,
okay,
and then you can do all these bounds. Yeah. Yeah, for the domain. Yeah.
Yeah.
Yeah. So what happens if we change the target instead of the domain? Well, so back at the beginning, I talked about what happens when you change the target to a Banach space. You have to worry about uniform convexity. You have to worry about this question of if I have a curve which is close to a line, or sorry, if I have a curve between 2 points which is nearly the shortest path between those 2 points, is it actually close to a geodesic between those 2 points? That depends on the metric, but you can do it to some extent in Carnot groups. The main difficulty is that geodesics in Carnot groups are no longer straight lines. Now there's some curvature. We saw this even with the Heisenberg group. The geodesic between 2 points on a vertical line isn't the vertical line. The shortest path between these 2 points is some path that spirals around. And so there's some more work to do because so you can still do these sort of arguments. The main difficulty is that now you want to say that if I know that the main difficulty is, or one of the main difficulties is the one-dimensional case. If I have a Lipschitz map from the real line into a Carnot group, then I can say that it's close to a geodesic on a lot of intervals, and then you also have to say that when it's close to a geodesic on an interval, then it's close to a line on a smaller interval. Because even though there's some curvature, it's close to it's close to a line on smaller segments. You may, I don't know. I haven't actually tried this, so I can't say for certain. But you may run into problems, but they can probably be overcome.
In this case, again, turning back to the rigidity, do you always need that at least one of the group is RK, or you could also move to the case of two groups, two collate graphs?
So I've just been stating very special cases of Ponceau. So Ponceau actually proved a theorem for Lipschitz maps from one Carnot group to another Carnot group.
Exactly.
And yeah, I believe that if you have, I guess the version you would prove is that if you have a bi-Lipschitz map between G and H, where G and H are both Carnot groups, then it's Ponceau differentiable in the sense that it's locally approximated by homomorphisms from G to H. And so if it's bi-Lipschitz, or if it's a bi-Lipschitz embedding, then there has to be a homomorphism from G to H, which is a bi-Lipschitz embedding.
An isomorphism in this case, yes.
Yeah, so in this case, there isn't one because the target is abelian, but in other cases, there might be.
Okay, thank you.
Other questions? Okay, if not, let's thank Robert again. Okay, so welcome everybody to the second lecture of the course of Francesco. Okay, so please go.
Yeah, Chiari non mi riesce a mettere con questo. Ok. During the first lecture, we have discussed the Plateau problem as formulated by, well, we have discussed a lot of things. I mean, we have discussed a lot of things about minimal surfaces, Plateau laws, and various formulations of the Plateau problem, etc. And today we're going to discuss this soap film capillarity model. So our point of view, our reason to introduce minimal surfaces was the modeling of soap films. And then we have discussed how this modeling of soap films is not just minimal surfaces, because you observe these canonical singularities that Plateau has essentially said, okay, it's y points, and then these points of type y can either form closed curves of singularities or can be singularities with endpoints. And if you have an endpoints, you're observing a tetrahedral singularity. And this is not, of course, inside H equals 0. So it's still compatible with balance of forces, and this essentially is the definition of stationary varifold, zero mean curvature in distributional sense, something we have seen. And we have introduced the notion of angular minimizer. Okay, so the limitation of this model of soap films, so minimal surfaces joined by Plateau singularities, is that it's not adequate to, as written on the slide, for studying the stability of soap films. Because, I mean, according to physicists and engineers, the instability of soap films is actually due to the three-dimensionality of the films. So the two basic mechanisms are the thickness of the film, which you can relate to the temperature. And so films have as a thickness, I don't remember how much is that. It's like in the order of micrometers. And this very thin layer of liquid is constantly exchanging particles with molecules with the surrounding media, the air of the room. So in a sense, there is already a mechanism of instability there. If you raise the temperature and the higher the number of transitions, evaporation, and then essentially there is the likeliness of somewhere in the film a hole being formed. And then as soon as you have a hole, as you know, there is the surface tension pool that is going to make the film move. And again, this is something that people have taken picture of. So you can take a picture of a film as it retracts and it bursts, okay? And measure how fast that happens and so on and so forth. And another reason, which is important, definitely in the study of foams, that is a more general kind of structure than soap films, but it's related. So in foams, you have surfaces not just with zero, but also with constant mean curvature, and they're joined by these Y singularities and T singularities. And now, what physicists and engineers postulate is that around the singular points, there is a large amount of liquid that goes there, and this liquid is moving. And then under the action of gravity, it drains the film. And so essentially, they want to understand how much, when you create a foam, how much it takes to drain and start losing bubbles and structure. Because it's kind of a game of time scales. They want the foam to solidify when it has a lot of bubbles so that it retains the mechanical properties of whatever the reason you're spraying a foam, say in a wall. Okay, acoustic isolation, let's say, okay. But if by the time it solidifies, you have lost all the bubbles, you have sprayed nothing in the wall, and so the point of the thing kind of, okay. So that's more or less, I think, the idea that's surrounding this thing. So there is, I think there is an even simpler remark about why, as a model, is clearly physically limited, and the remark is that it is a scale invariant. So if you have a minimal surface and you take the scale of this minimal surface by a huge factor, it's still a minimal surface. So it's like saying, let's imagine that we have a wire frame that we can expand at will, okay? And so we create a minimal disk, a disk of soap spanned by this thing, and then we start making the wireframe larger and larger and larger and larger and larger and larger, and it still says h equals 0. I mean, it doesn't matter. 1 kilometer of wireframe is still h equals 0 and the solution exists. So it's clearly, in a sense, okay, limited from this viewpoint. So, and that's where this story of dry and wet soap films starts. Okay, so in the books, in the physics and engineering literature about soap films, they have this double terminology. So they talk about dry soap films that are two-dimensional minimal surfaces joined by Plateau singularities. And then they have what they call wet soap films, which are a much weirder object because they are an object with mixed dimensionality. So what a wet soap film is 2D minimal surfaces, but they're not joined anymore by Plateau singularities, so by lines and points. They're joined by three-dimensional regions with negative mean curvature. So for example, here, that's a very important picture because here you see a y point, that would be the 3 half planes. And then when the y point becomes that's a dry y point, if you want. If you make a wet dry point, you don't see anymore the 3 half planes joining along the line. The 3 half planes stop well before the line, okay? And then there is 3 cylinders with constant mean curvature, of course, right? That join these half planes. And they have negative curvature and they attach tangentially to the planes. And then this kind of wet y point is assumed somehow to wet T points. I have seen no claim in the literature that wetting of T points happened by a unique solution of some PDE or ODE. They just draw something like that. I drew this picture based on their pictures. So they draw something like that. But there is apparently no theorem. So what I'm trying to say is that why it seems to be a canonical way to wet a Y singularity. I can't imagine another way, honestly. So, and must be pretty easy to show that's the only way to wet a canonical a Y singularity. I haven't seen any claim about this is the unique way, kind of the archetypical way of wetting a T singularity, okay? But they draw pictures like that. So where they give us something more precise is the transition law for these Plateau borders. So first of all, they call them Plateau borders. As far as I know, they are not displayed in the work of Plateau. So it's like by extension of what Plateau described, they introduced the terminology Plateau borders. And these Plateau borders, they have a conjecture on how you have a transition from constant mean curvature, that is the Plateau border negatively curved, from constant mean curvature to zero mean curvature, which is the smooth minimal surfaces. And the assumption they do is that the unit normal changes continuously across the transition lines between wet and dry interfaces. In particularly, there are lines, okay, where the second fundamental form of this object jumps and you go from constant to zero mean curvature. So they assume this happens on a one-dimensional object that has a differentiable structure and that the normal goes through continuously. So this is like page 10, okay, in the books they write. Then after they assume these, they go on and do stuff like writing the Navier-Stokes equations inside the Plateau borders, transform them into an ODE, and compute how long it takes for the liquid to drain and the thing to burst, okay? So that's it. So that's not discussed anymore. So this is from the physicist engineer's viewpoint, that's the end of the story. Of course, from I would say from the point of view of mathematicians, it's more like, okay, you want to derive all these assumptions, at least the question for me arises, right? I mean, how is it that the models that we use, area minimization, are going to predict, kind of lead us to observe these things, right? So, and I don't know, I mean, how do you model it, right? I mean, it's not that, I think you don't want to start modeling them by working on a class of objects that it's a bit of sets and a bit of surfaces like that, you know? So why is this thing arising naturally? And it's not just a crude phenomenological description of what you think you're observing, okay? So that's at least the mathematicians, I think, viewpoint on this. So which model do we use? So wet films are mixed to two 3D objects which hold the positive volume of liquid. That's the first remark. And liquids at equilibrium in a container are studied with Gauss capillarity theory. So this is the basic fact. So the conclusion, I guess, is that we want to study these objects by using Gauss capillarity theory. Okay, so the idea is trying to observe these objects, these soap films spanning a wire frame, the wet version. They should arise by working with capillarity theory. Capillarity theory is in physics liquids at equilibrium, and it's capillarity theory. And then somewhere inside the energy landscape of capillarity theory, there should be a way to observe these wet soap films. Okay? Now, what is capillarity theory? Because maybe you haven't seen it yet or recently. So, in capillarity theory, indeed, you have a liquid resting at equilibrium inside a container. So in this case, the container is denoted by some open set omega, and E will be the region occupied by the liquid. And the two objects that matter in capillarity theory are the liquid-air interface and the liquid-container interface. So the liquid-air interface is the boundary of E inside of omega, here this blue line, and the liquid-container interface is this purple line, boundary of omega intersection boundary of E. Okay? And then both surfaces are subject to surface tension. That's the physical assumption. And now the surface tension of the two interfaces doesn't need to be the same, because one it's a liquid-air interface and the other is a liquid-solid interface, right? So essentially, we have already discussed why area is related to surface tension, right? So the derivation with the lateral pull, the tangential divergence theorem, and so on and so forth. So evidently, you pick two constants, sigma 1 and sigma 2, you put them in front of the area of the two surfaces, and that's your capillarity energy. The first constant, sigma 1, is positive. The second constant doesn't need to be positive, can be positive or negative. The second constant, the one in front of the liquid-solid interface, is in absolute value smaller than the surface tension constant of the liquid-air interface. So this is an assumption that is stated matter-of-factly in the physics literature. It's like you measure it and it's like that, so why worry? From the mathematical viewpoint, you can say this essentially. If the second constant is less than minus sigma 1, then you have then essentially you want to use as much as you can the boundary. And so you have global minimization will give you something that wets all the boundary and then, okay? If conversely, sigma 2 is larger than sigma 1, then you avoid the boundary at all costs, and you just have a droplet inside the domain until the volume, total volume, allows you to do that. So, and then you start entering into mathematically degenerate problems, and I don't know anymore what happens. But in a sense, from the point of view, if you want to talk about this model in a physical regime, you're absolutely fine assuming that this sigma 2 is in absolute value less than sigma 1. So which in particular means you only need one, the ratio of the two. So the minimization problem is we minimize the capillarity energy with 1 in front of the liquid air interface, some alpha between -1 and 1 on the liquid solid interface is a subset of omega with given volume V, right? So, and this is a very classical problem. When alpha is equal to 0, this problem becomes the relative isoperimetric problem, which is important when you study Sobolev-Poincare inequalities and all sorts of estimates in domains, okay? And so the Euler-Lagrange equations are very similar to the equations of we have studied 1 moment ago for the wireframe. Now we have a volume constraint that we didn't have before. So the equation is not going to be zero mean curvature. It's going to be constant mean curvature for a constant that could be positive or negative, okay? And this constant mean curvature is for the liquid air interface. Of course, the liquid solid interface, it has the mean curvature of the container. I mean, it's not that you have a condition there, but you have a condition at the contact points. So if you imagine boundary of omega intersection boundary of V as a surface with boundary inside the boundary of omega, okay, at this contact line between the droplet and the container, you have a constant angle condition. So the scalar product of the outer unit normal to the droplet and the outer unit normal to the container, mu of omega scalar nu of V, is equal to alpha, where alpha is the parameter that here I haven't, well, I guess I can fix it now. So, is the content, yes. What? So this is you consider the boundary. Oh, thank you. Yeah. You're right. Yeah. Okay. Looks better. So this is so if you have a minimizer, these are going to be the Euler-Lagrange equations, okay? And in Y generality, you have a minimizer. So it's like you don't need to sum that much to get a minimizer from this thing. Yes. Mm-hmm. Yeah, so what you will get is that alpha in absolute value is strictly less than 1. Yeah, for alpha greater or equal than 1 in absolute value, you may have either non-existence or it's sort of a degenerate problem that is not, I haven't seen ever much discussed anywhere. By physicists, definitely because they don't care, because I think this sigma 2 is always, yeah. Okay. Exactly. You start having a degenerate problem. I don't know. I mean, which is not physical interest. So I mean, you can ask yourself every question you want in life, but right. So yeah. So, but it's not. I'm going to put alpha equal to 0 in a second. If you are concerned about alpha. So and I like the alpha because there is a lot of cool stuff that happens. But when you have the alpha around, and I'm studying it right now for these problems. But let's put alpha equal to 0 because there is already a lot of action with alpha equals 0. So let's say with alpha equals 0, we have this problem. Now, what happens when we apply this alpha equals 0 model to soap films? So this is a bit weird. So it requires a moment of an effort, okay? Because we say that omega was a container for a liquid at equilibrium, but what is the container for a soap film? It's a very weird container because it's the boundary of the wireframe. So it's the R3 minus W. Our wireframe was W, right? Was some closed set. And then in the complement of W, which is an unbounded region, is the region accessible to the soap film. And the soap film will be a liquid at equilibrium in the complement of a wireframe. But if you just say that, actually a liquid with small volume, because definitely whatever is that happens with thickness of subfilms, the total amount of liquid, right, is going to be a small parameter. So, but if you do that, if you do Gauss capillarity theory at small volume, all you're going to observe is something very close to a hemisphere sitting somewhere in the boundary of your domain. Essentially, it goes at the point of a highest curvature, highest mean curvature in the boundary of your domain, of your container omega. Okay, so definitely you don't see soap films if you take capillarity and put the volume V small. You observe small droplets sitting somewhere on the wireframe. Right? So that's absolutely expected and not surprising. I'm not claiming that this is, but it's just to tell you, I mean, we must use capillarity theory. We are definitely at small volume. The container is the complement of the wireframe. All these things are certain. Okay, there is no doubt about them. But what the model says is you have a small round droplet sitting somewhere. So you need to come up with something different. And as you can imagine, since we have spent 90 minutes talking about homotopic expanding conditions, what I'm going to do next, okay, is to impose the homotopic expanding condition on this droplet, okay? So, so for those, let me see, for those that weren't here, so let me see if I can find just a super quick recap on what this homotopic expanding condition meant. So, so when you have a closed set that will play the role of the wireframe, you can fix any class C of embeddings of S1 into omega, the complement of the wireframe, and you ask your class to be closed by homotopies. So in the moment that I put one curve gamma inside the class, all the homotopical images of this curve are contained in C by definition. Okay? And if you have, say, you start having not just one W here, but you have, say, various tori, okay, you may have curves that just loop around one or that loop around two and so on. So you may have many different classes C that are closed by homotopies, okay, that you may want to consider. And so spanning with respect to a given class means that, so a set S is C spanning W if it intersects non-trivially all the curves in the class C, okay? So this was our definition, right? So we are going to use this definition to force the droplet to span the wireframe. So this is just a reminder from what we discussed the other day. So, and this is the model. So the subfield capillarity model, or at least the first thing you want to try if you're familiar with Harrison and Pugh, is imposing. So up to here is just classical capillarity theory. So this is Gauss capillarity theory with alpha equal to 0. And then this is the Harrison-Pugh condition imposed on the liquid-air interface. So why am I imposing it on the liquid-air interface? I could have imposed it on the set E, the closure of E. Why haven't I done that? There is no reason. So you have two different models with different properties, okay? And it may happen that they have the same difficulty level. It may happen that one is a bit easier than the other to study. Some years later, you will discover that it would have been much better to impose this one. This is simpler. But unfortunately, I didn't. Okay, so this is a model that we started studied with Antonello Scardicchio, a physicist at ICTP, and Salvatore Stuvard, who at the time was a postdoc in Austin. So, okay, first of all, droplets are not admissible, as you can see, because clearly they don't intersect all the curves, gamma in the class. And so this is the first conjecture. For example, with two disks, you know that the Harrison-Pugh minimizer is just a segment between the two disks, right? So at small v, minimizer of this thing should be a sort of sandwich trapped by two circular arcs of small mean curvature. So kind of a set with constant mean curvature. Oh, what's going on now? Why did you do that? Ah, okay, because it's in the low battery mode. Okay, no, we cannot keep it in the low battery mode, otherwise it. No. Il Mac ha tutta la batteria del mondo. Il problema è che. Ah, non so come collegarlo al Mac, però. Ah.
Anche lo schermo assorbe proprio del...
Aspetta, no, ma questo c'ha questo tipo di attacco. Sì. Aspetta, no. Aspetta, questo qua no, però. Questo qui è così, però il problema è che la parte finale del cavo è questa, quindi non l'attacco all'iPad. Così. Ok. Non è semplice questa cosa. Ok, questo attacco. E poi?
Questo è tu.
Ok, questo è partito? Sì. Va bene. Però non ho capito perché ha smesso di fare sharing lo screen. Ah, ok, start broadcast. Ah, perché quando è andato con la batteria in pausa, ok. Stiamo facendo una cosa di una complessità. Ok. Andiamo, eh. A posto? Ok. Ok. Allora, i minimi del problema a volume piccolo con due dischi dovrebbero essere questa coppia di curve con curvatura. Ah, I'm sorry. No, because I was talking with the. Okay. So, okay, I have to find again the seminar. So, yes. We have the Plateau minimizer is the segment, and for small volume, okay, that's what you should observe, right? Something with constant mean curvature and the 90 degrees condition as it attaches to the wireframe. So more generally, there are other situations where you may expect to have something that nice. So for example, if you have a convex domain and the wireframe is the epsilon neighborhood of the graph of a smooth function over the boundary of your convex domain, there is essentially only one minimal surface you can observe, even in the context of stationary variables. So you have a super strong uniqueness theorem. And that minimal surface is going to be the solution of the minimal surfaces equation. It's like no other option. So it's going to be a smooth graph. So in that case, a natural conjecture is that minimizers of these problems will have this liquid-air interface in the form of two graphs over these minimal graphs with small constant mean curvature. I still have the echo here that it's a bit annoying. I don't know how to kill it. Okay. So when we first looked into this model, before even trying to prove existence for this SOAP film capillarity model, we wanted to understand better this problem of surfaces with small mean curvature. So essentially the question is, if you start from a wireframe and you have, say, a unique minimal surface spanned by this wireframe, as is in this case, do you have a compactness theorem for surfaces with vanishing mean curvature? And how this compactness theorem should look like? So the first theorem that we prove is the case of almost minimal Lipschitz graphs, which is the happy case, okay, in a sense. So the first case you want to understand. So here we have a smooth compact minimal surface with boundary W, and we assume our surface is strictly stable. So it's not just a minimal surface, it's not just a stable minimal surface. That is what we introduced the other day. But it's also strictly stable. It means that the second derivative of the area functional is actually, with a positive constant lambda, is actually strictly coercive as a quadratic form in the space of the normal variations to the surface. Okay, then we consider any surface M that comes as a normal graph. Nu S is the choice of the normal of our orientable minimal surface. So it's the normal graph with a function u, and we assume the function u to be small in C0 and small Lipschitz constant, and 0 at the boundary of S. So this is the simplest kind of almost minimal surface you may want to think about. So in this class, you can prove an inequality that is actually a sharp inequality in terms of powers involved. And the inequality is that you can control the area gap between these two objects in terms of the L2 norm of the mean curvature of the graph M. So this is the kind of inequality where the derivative of the energy controls the distance of the energy from the minimal energy, right? And it's an interesting inequality because it's sharp, okay? Okay. You have this inequality, and also, but then applying PDE regularity, you also can control not only how far M is from S in area, but also how big is U in terms of its C0 norm. Okay, you can control that also, but to do that, you need not only the mean curvature in L2, you need a bit of mean curvature in LQ for some Q larger than N over 2. N over 2 is not too bad. So the exponent that trivializes a bit all of this story is any exponent larger than N, strictly larger than N, because those are the exponents of the regularity theory of Allard. So you have theorems that, in a sense, quantify graphicality for you. Here, we are all powers involved here, 2 and Q for Q larger than N over 2 are potentially powers below that. So the theorem is a bit more interesting than it may look. The reason why this exponent 2 is nice is because is the exponent for the dissipation inequality of the mean curvature flow with fixed boundary. So if you do the gradient flow of the area functional at fixed boundary, and you compute the dissipation of the gradient flow of the area functional at fixed boundary, and you compute the dissipation of the flow, the dissipation of the flow is the L2 norm of the mean curvature. And then when people proves, I mean, the archetypical proof, you never prove it like that because it's always too difficult to have the general theorem, but the archetypical proof would be showing that the dissipation controls the gap in energy linearly. When you can do that, you have exponential convergence. So if you want, this is the sharp dissipation inequality that implies exponential convergence for the mean curvature flow with boundary, okay? So this is the first theorem that we prove, and essentially it's trying to understand the situation where you're already very close to the surface. And then we have another theorem. I mentioned these theorems not because they're particularly, in my opinion, particularly, how to say, strong or sharp or applicable. So they're not fantastic theorems, in my opinion. I mean, there is clearly a lot to do. I'm mentioning them because there is clearly a lot to do, okay? So in a sense, the general question of understanding almost minimal surfaces and their convergence to minimal surfaces seems a very rich question. And as far as I know, these theorems are the two theorems out there that try to address a bit what goes on, but they are by far not exhaustive of what you may want to say. The other theorem that we have, so it's trying to address the situation, the general situation, under some assumptions. So the first assumption is that our wireframe W is compact and orientable, and is such that the Plateau problem associated to this wireframe is finite and smooth. By this I mean that finite means that there are only finitely many minimal surfaces generated by this W, and if you wonder, there are out there choices of W for which you have infinitely many possible minimal surfaces, okay? So we want to avoid that, just to have a situation that is reasonable, okay? And then second assumption is smooth in the sense that all the area minimized, so there are going to be finitely many area minimizing surfaces generated by this W, and they're all going to be supported on smooth surfaces up to the boundary. So this would be the precise assumption. So here for the slide is finite and smooth. Okay. Then the second assumption is more interesting, is a sort of barrier condition. So the condition is that consider W and consider its connected components. So what you want to be able to do at each point of W, for each connected component, at each point you want to put a acute wedge that contains in its interior all the rest of W. So this is a good W, these two circles are a good W. This W here is a bad one, because at this point X, if I want to put a wedge at X and contain the rest of W, the wedge has to become obtuse. It has to open like that, okay? In order to, can you see that? Right? So these are the ones we can treat. These are the ones that we cannot treat in our theorem. So it's a sort of uniform convexity assumption of sorts, but without any convex set being explicitly mentioned, I would say. Okay? And then, with this setting, we consider a sequence of surfaces, MJ. So the MJs are compact, orientable, nice, bounded diameters and bounded areas, otherwise you don't even start. Their boundaries are converging in C1 to W. They don't even need to have the same boundary. The boundaries can just be C1 deformations of the boundary of the wireframe we want to work with. And their mean curvature goes to 0 in L1, which is the weakest kind of almost minimal surface control you may want to impose. So under these assumptions, you can prove the best theorem you may expect to hold. So you can prove that there is a limit minimal surface bounded by W, S, and there is a sequence of open sets, EJ, such that if this is S and these are the MJs, notice that the MJs and S don't have the same boundary. So here in orange, I have a kind of the boundary of EJ, you see, we'll have also an orange part that is not part of the MJs and it's not part of S, kind of to join them. And you can choose these sets EJ so that their volume goes to 0, and the area of the part of their boundaries that is not either in S or in MJ that you need to close the gap goes to 0 in area. So this would be the convergence, the flat convergence of currents, if you want to use the esoteric terminology of GMT. It's that picture. And now you see why the barrier assumption is important, right? Because imagine that I take something that clearly violates the barrier assumptions, like two circles, two concentric circles. So clearly the barrier assumption doesn't hold because I cannot put a wedge at the points of the interior circle and containing the rest of the wireframe, right? Obviously. And here it's very easy to do something like a sequence MJ of stuff that rises, say, like a catenodal neck, and then it goes back and does this, right? So, and this sequence of surfaces is going to converge to minimal surfaces, of course. But you see, a minimal annulus with multiplicity 1, and then you cover also a minimal disk in the interior with multiplicity 2. So you have convergence with multiplicity. So if you want convergence, straight, honest to God convergence to one singular to a single minimal surface, okay, you need something, and this barrier assumption gives you that. Okay, gives enough control on the geometry that you don't have what we have called bubbling, not because there are bubbles involved, but because this kind of concentration phenomena are known in the geometric calculus of variations as bubbling because they are being first studied in the Yamabe problem, and then you have something that makes sense to call bubbling in that setting. Okay, and then, and this is really a bit trivial, so if the mean curvatures are bounded in LP for P larger than N, so that Allard works, then under the above assumptions, your MJs are graphs over S, with C1 norm goes to 0, and therefore if S is strictly stable, you can go back one theorem, and you have the sharp decay rate that I mentioned with the L2 norm. Okay? So, is this satisfactory? I don't know. I mean, it seems like essentially it's one theorem where we do all the basic things. We do all the obvious things. If you know variables, currents, and so on and so forth, we do all the basic things that are obvious. We have this barrier condition because clearly otherwise you have counterexamples. And so this was the first one that came up as a way to kill all the problems in the proof. But I would say it's a very open problem, right? And I think it's interesting because even if you assume graphicality, right? The smallness of the H2 norm, the L2 norm of H doesn't imply graphicality. So how do you show convergence there? This, even when the limit surface is a circle and the disk, seems to be delicate to prove. I wouldn't know how to prove it. So I think there are some interesting problems on this direction. Okay, so now we can go back to the soap-thin capillarity model. I did on purpose waited to give you example 2, just dwelling on example 1 and on this smooth convergence and so on and so forth. Example 2 tells you more realistically what you should expect. So I have my 4 disks, and now I'm trying to have something with small volume that somehow spans the 4 disks. And then my poor droplet is forced to have 4 tentacles that reach to the disks, right? And then somewhere in the middle hold this volume V. So the conjecture is that it should look like, for small volume, the minimizer of the Plateau problem. And the minimizer of the Plateau problem, as we have already discussed, is going to be 2 y points joined together. So it should look like that. But then, you see, what were sets EJ seems to converge to something of mixed dimensionality. So you will have a set, you have that the sets EJ will converge to a set E, but the set E will just be the union of these curvilinear triangles away from W. So the limit set E, the boundary of the limit set E is not C-spanning anymore, right? Because there is a gap between the region where this guy is and the wireframe. And then there is this limit object K that we define so that it contains the boundary of, so K, we define it so that it contains the boundary of E, okay? And K is C-spanning W. So that's how it works, okay? So the fact that my boundaries were C-spanning W is not lost, but it's like they collapse with multiplicity 2 on this K, okay? And the limit object K, we should have 1 dimension less, which would be a surface, it's still doing the C-spanning for you. So at least on these little examples, you can convince yourself that you may have a model that eventually will capture this mixed dimensionality and this thing that the physicists want to use. Okay, then you try to prove a bit about it. And this is a theorem with Darren King, who was a grad student with mine in Austin, and Salvatore again when he was a postdoc. We wrote these 3 papers. So you have your soap-thin capillarity model. Now I'm trying to be a bit more precise. The boundary of E has become the reduced boundary of E, which is a technical notion. So it's like the part of the boundary of E that has an approximate tangent plane. So that has a decent measure in a measure theoretic property of differentiability. It's a kind of very weak property, but important. The C-spanning is done by the closure of the reduced boundary of E. So first of all, we have existence of what we call generalized minimizers. So are these pairs, kappa E, E has the right volume, is an open set. The closure of the reduced boundary of E is contained in the set kappa that is closed, and kappa is doing the C-spanning for you, okay? The limit energy, psi V, is equal to twice the area of the collapse region plus once the perimeter of the set E, as you would expect. So the initial energy was just the perimeter of sets, okay? Now the effective energy is the perimeter of the limit set plus twice the area of the collapse region. Because energetically I was paying that with my EJs, and so I cannot forget about it. Notice that these are generalized minimizers, not minimizers. So if I have a pair KE, I cannot just do something like I change a bit K, I change a bit E, I have a new pair K tilde, E tilde, and I compare the energies. So I have first to do that. I have K tilde, E tilde, and then I have to find sets F, okay, that have similar energy to K tilde, A tilde, and are admissible in the problem. So this sort of generalized minimality property, I didn't prove that Ke minimizes this energy among all competitors of that form. Okay, that's not what I was able to prove. Every time I have to go back to the original class. I'm mentioning this because this is actually a huge problem, because it's not easy. So when you have something of mixed dimensionality, proving convergence in energy to a pair Ke means essentially doing a sort of epsilon neighborhood argument and started trafficking with Minkowski contents. So it's convergence of Minkowski content to Hausdorff measure. And we have done pretty fine stuff in that direction, also building on a paper of Ambrosio, Villa, and Colesanti. But it's really a point where it limits greatly the kind of analysis you can do. So now I'm mentioning this because at the end of the day, really, it's all in the details, okay? The fine line between proving something and not proving something. So this is a point where this thing is really delicate, yes? Oh, yeah, for sure. Yeah. So K minus the reduced boundary, it's really a region of positive measure of its own with its different properties than the reduced boundary. Absolutely. We're going to see more of that. So the second theorem is that these generalized minimizers, if you consider them correspondingly to volumes Vj's that go to 0, you expect them to converge to something in the Harrison-Pugh-Plateau problem. Otherwise, there is a big problem, okay? And luckily, that's what you can prove. So if you take a sequence Vj that goes to 0, generalized minimizers for volumes Vj that goes to 0, then there exists a minimizer S in the Harrison-Pugh problem such that the radon measures that you naturally associate to this Ke, that are K minus the reduced boundary of Vj with multiplicity 2 plus Hausdorff of the boundary. So these measures converge weakly star to twice the minimizer in Harrison and Pugh, seen as a radon measure. Twice because you are collapsing on it, right? So you can prove that. And let me stress, in particularly the effective energy as the volume goes to 0 goes to twice the energy of Plateau, which is fine. But let me remark that this is a very weak notion of convergence. So this is not even convergence in the very full sense. It's just convergence in the sense of radon measures. So all sorts of weird tentacles and dust and noise could still be there. So it's very, very far from what you would expect to be able to prove. I will comment much more on this thing. And then there is the regularity theory that you can prove. So here you're really a bit fighting because the reasons I said before. But what you can prove, let me first of all tell you what you can prove in this setting. So first of all, you can prove that K outside of the closure of E is a smooth minimal surface. This is more than what you would get from a straight Allard, because even just from straight Allard out of the box, this K minus closure of V could have a closed singular set of area 0, Hn0. So this is much more. And I will tell you how you do that. Then the reduced boundary, the part of the droplet that is reduced boundary, is a smooth constant mean curvature hypersurface. This is Allard and easy. We will prove in a moment that if there is collapsing, if K minus the closure of V is non-empty, if there is a collapsed part outside of the droplet, then this lambda is less or equal than 0. So this negative curvature that the physicists observe appears very early in our analysis. And then there is the transition region. So from the reduced boundary to the closure of the reduced boundary, and this is exactly Allard. So this is the point where we don't have there is a jump in the multiplicity of these variables, okay? This object has empty interior. So, and this is really bad because, I mean, the physicist, this is the transition region between constant and zero mean curvature. For what the physicists are concerned, that's a line. What we get is that is meager. So, there is okay, there is a bit of distance to cover there. Okay, so seems to have twice the same 3 times, oh no. Yeah, okay. That's an interesting remark. So this theorem doesn't exclude interior collapsing. So that's very weird of this model. So the collapse region K, in my pictures, it always comes as something that contains the boundary of E, okay, and then sits outside E. But nothing forbids, in what I'm saying, that something like that happens, right? That here I have E, here, which it will do whatever it wants to do, but for some reason, there is some interior, so there is a piece of K that lies inside E. Nothing forbids that. And, but one say, okay, that's trivial. Why you would do that? It doesn't help with the spanning, right? And then if you try to prove it, you enter into a weird series of consideration about the wet part trying to wrap around the wireframe. And then if they do that, you may need actual interior collapsing to do spanning. And for large volumes, actually, it seems that this may actually be a smart thing to do at times. So it's a very fishy thing, okay? This possibility of this interior collapsing. And it stayed there for a while, okay? So, collapsing. Collapsing means, the definition of collapsing is that there is some K outside of the closure of the reduced boundary of E. Could be inside of E, could be outside of the closure of E. Exterior collapsing is that when you have some collapsing outside of the closure of E. So the first question is, what about possible parts of K inside of E? This interior collapsing. So the first problem is exterior collapsing the same as collapsing, as we all would expect, at least for small volume. Then, how do you prove that lambda is less or equal than 0? Let me show you the proof, because a sketch of the proof, because this is really fun and gives you an idea of the kind of arguments, as I did the other day when I did the CAP competitors, right? It gives you an idea of the kind of arguments that are actually behind these theorems. So let's say that we have our collapse part with multiplicity 2, and then we have the wet part with multiplicity 1. And now, for some reason, E is constant mean curvature, but it has positive mean curvature. Okay, so it's kind of a Rham. So what I can do, I can push up. So remember that here I have multiplicity 2. So I can create a competitor by pushing up K and adding. Okay. Yeah, okay, let's do it like that. First I push up. When I push up near a point of K minus closure of E, I can increase by epsilon the volume that my configuration encloses, right? And how much do I pay? I don't pay linearly in epsilon. Why? Because the mean curvature is 0. So the first order in the area expansion is trivial. I pay quadratically in the volume that I am adding because I activate at worst, the second order in the Taylor expansion of the area. So that's a convenient deal. I add an epsilon of volume at an epsilon square cost of area. And then I can adjust this by pushing where the mean curvature is positive. This is going to cost, right? But it's costing linearly. It's costing linearly. So because it's a positive constant. So if you do the area balance, right, you gain linearly in area. You gain because you are making it shorter, because it's kind of convexly curved and you're making it shorter, okay? And at the same time, in area, you are increasing at most quadratically, so you always gain. It means you are not a minimizer, okay? Of course, this argument doesn't work if lambda is 0 or negative. It goes in the wrong direction. But if lambda is positive, okay, you are allowed to gain area at a linear cost in the volume, but then you are allowed to recover area in a quadratic cost of the volume. And so it's always convenient, and you are never going to have lambda a positive, okay? And then what is the proof? So you have these variations, which I think are cool because these are not mappings variations. So you see, these are not the mapping that is not, you remember the Almgren minimal sets. I mentioned that the key point in Almgren minimal is that the maps that you use are not injective. But these are non-mapping variations. Here it's like you have something with multiplicity 2, and you are detaching one sheet of this thing from the other. So these are not mappings variations. There is not a function. It's kind of more geometric variations. And once you have done this thing, you need to do a Minkowski approximation to get the effective energy, because remember, you compare with sets. So I need to construct a set that will have this energy. So, and that's why first I have to prove all the Allard regularity I can, and then I have enough regularity and density estimates to try to do Minkowski arguments on these things. So let me skip the regularity part. Enough regularity. I will just show you briefly this picture. So this is the proof on why K minus the closure of V is smooth. The idea essentially, very quickly, is that if K minus the closure of V has a singular point of any kind, then it has a Y singular point. This is the theory. This is implied by some work of Colombo, Eder, and Espolaur. Once you have a Y point, you can wet the Y point, saving energy. So you have a energy adding variation that saves volume. And then, since you know that you have negative mean curvature in the wet part, you can adjust that with a cost that is less than what you are gaining by wetting the singularity. So this is the argument that tells you, if there is singularity in the collapse part, there must also be Y singular points. But a dry Y singular point is never a good idea. Whenever you have a dry singular point, you can wet it and use the lambda negative elsewhere to gain. End of the proof. Okay? So, yeah, and in this way you prove that the exterior collapse part is smooth. It doesn't have singular points at all. So at the end of the day, after this theorem, the only singular points in this model can be in the interior collapse part, should it exist. It doesn't seem possible, but and in the transition region. And what is really dramatic is the transition region, because the transition region should be a region where you go from smooth to smooth with a normal that varies continuously, and just the derivative of the normal jumps, right, on this line, and instead it's a meager set. Okay, so yes. Yeah, exactly. The point is, no, this is clearly not the, so this picture is just to visualize. It's not the right kind of thing. So the problem could be if for some reason, imagine that, it's really hard to imagine, but imagine this is W, okay? And for some reason, you want to wet some part of W with E, okay? And then, since you are just asking that the boundary of E is doing the spanning, if for some reason you're not spanning anymore, so you need to add a little piece of K somewhere to do the spanning for you. I don't believe it, okay? I don't believe it, okay? But, or it could be that for very large volumes, it's better just to look like a gigantic ball and do the spanning in some fishy way using internal collapsing. I don't know. So this is not something that is convincing me. I don't believe it's possible. All the attempts of proving it, kind of failed. Otherwise, I would have the theorem. So I don't know. I don't think it's true for at least for small volumes. And it looks really counterintuitive that it should do that. But excluding it, it hasn't been possible until recently. But this is tomorrow's lecture. And it doesn't come for free. It comes with changing the rules of the game a bit. So, okay. Okay, let me do a recap of the open questions, okay? So, no interior collapsing, we just discussed. Then there is something that is called the non-collapsing conjecture. So, the conjecture says this: if all the minimizers in the Plateau problem, in the Harrison-Pugh Plateau problem, are smooth for some reason, for example, because W is the graph over the boundary of a convex set of a function, okay? Then the conjecture is that you shouldn't have collapsing. Why would you, if you are converging to a nice graph, why on earth would you want to do triple points? I mean, it's wetting in general, right? So this is the conjecture. It has been proved recently in the case where W is a planar curve. So W is the epsilon neighborhood of a planar curve. So the minimizer in Hesselin-Pugh is just a piece of plane filling this thing. So you cannot make it simpler than that. So proving it in that case is a paper by Bevilacqua, Stuvard, and Velishkov, where you have to do some delicate free boundary problems. Velishkov is a super expert of free boundary problems, okay? So you have to do some delicate work with free boundary regularities to nail down the proof. So that's just to say that this even in a relatively looking tamed case like that of graphs, is not immediate. Even if you make the graph flat, it requires considerable work. And I hope to talk more about this one later. Then another conjecture is what we have called the wetting conjecture. In the case where there is at least one minimizer in Harrison and Pugh with singularities, and we know already there are examples where you have both, right? So there are examples where you have non-uniqueness, and you can have like 4 disks in the plane, and you can join them by lines, or you can join them by 2 tripole points with the same cost. So this is a case where Harrison and Pugh has 2 minimizers, one smooth and one singular. So the conjecture is that whenever there is at least one singular, the minimizers in KJ, the generalized minimizers are converging to something with singularities. So the SOP-fin capillarity model, whenever possible, will always choose the one with Plateau singularities if available. And when it does that, the wet part is converging to the singular part. Okay? So if there is a y point, that's all you have, the wet part is going there. There cannot be some wet part nearby the collapse, the regular part of the Plateau minimizer. Again, it's very natural. You look at the pictures, you do the little examples you can do, okay? But again, proving it's another story. So, okay, and then there is the problem of unconditional convergence. So here I am stating theorems that are much more ambitious than step number 0. Step number 0 is, okay, in general, what you can say in terms of convergence. Remember that we just proved a sort of Radon measure convergence of minimizers in the generalized problem to minimizers in the Plateau problem. But that's very weak. For example, even varifold convergence is non-trivial. So a first question could be, can you prove at least the Hausdorff convergence of KJ? Can you prove at least the Hausdorff convergence of your wet film to the limit dry film? Okay. This, again, is another thing that we couldn't prove. And actually, so here is this little remark that tells you why even the varifold convergence is non-trivial. So think about the example of a single Steiner point in the plane, right? So in this case, if V is the volume, Vj is the volume you're constraining, you can compute what is the curvature of these circular arcs. And this curvature is going to be huge. It's going to be the inverse square root of Vj as the volume goes to 0. While the length of these arcs is going to be the square root of Vj. So if you do look at the mean curvatures of these boundaries, they are not only negative, they're going to minus infinity, they're going, and the LP norm of the mean curvatures is going to plus infinity for every p strictly larger than 1. And this is the most stupid example you can think of. It's a tripole point in the plane, okay? And even in this super simple situation, you don't have any good control on the mean curvature. You have the L1 control. However, this L1 control comes because of a compensation, which in general, it's, I don't know how you expect to prove it, right? Because it's sort of compensation between the region where it's large, but it happens on a very small region, and so it compensates. So this would imply the varifold convergence, which would be a bit better then, because it would be the convergence, radon measure convergence in position and in the sense of tangent planes. A bit better. So, and then there is the key open problem. If you play a bit with these 4 or 5 questions, I don't remember how many of them, you end up more or less quickly realizing that this transition problem is not just because the physicists assume, it's really one of the key points in all this story. You cannot really go far if you have this meager set, you know, with potentially with positive Hausdorff measure area going around your wet film. So how do we prove that? Again, what we proved so far is that it's meager, what should be n-1 dimension. So I have a question for Valentino, I guess. I have done 1 hour and 10 minutes. Is that enough, or should I talk 5 minutes more? Okay. 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 25 minutes. Okay. 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 Good. So let me go back a moment then. Let me go back a moment. So, since this is a school, let me go back a moment to the regularity of KE. So the amount of regularity that was proved in this paper, okay? So let's give a name to this effective energy that you are actually the one we are really working with. That is twice K minus the reduced boundary of V plus the area of the reduced boundary of V. So the generalized minimality inequality that we have, that is FKE less than perimeter of F for every F whose boundary is suspending, you can work a bit with it, and you can at least prove this. So you see, this is the minimality of KE in terms of the effective energy F with respect to every diffeomorphic variation. So these are the nicest variations you can decide to work with. You take a diffeomorphism, you move your guy, and okay, so you can't do easier than that. I mean, it's like, so this we can do. This means start from KE, look at the pair f of k, f of e, and then do the Minkowski kind of approximation argument and check that you can find sets that converge in energy to that and blah, blah, blah. So this can be done. Once you have that, you can do variations and you can prove the Euler-Lagrange equation in this form. So this is the equation that tells you that k minus reduced boundary of E has zero mean curvature in distributional sense, and that the reduced boundary of E has constant mean curvature equal to lambda in distributional sense. So this comes, once you have a comparison with all diffeos, you can deduce that. In the language of varifolds, it means that the varifolds with multiplicity 2 on the collapse part and multiplicity 1 on the reduced boundary has bounded mean curvature, because the mean curvature is either 0 or lambda, so it's not a constant mean curvature. So it has 2 problems, this guy. In a sense, it has non-trivial multiplicity because it jumps from 2 to 1, and it's fine. If the multiplicity is locally constant, you are fine. But where it's bad is where the multiplicity jumps. Then regularity is much harder. And then the mean curvature is not constant, is from 0 to lambda. Now you see it in distributional form. This is the Euler-Lagrange equation of this problem. Okay? So if you want, the goal is proving that this Euler-Lagrange equation implies what the physicists want. It will not. You will need to use minimality billions of times, okay? But it's part of that. And then what follows just by Hallard is that the reduced boundary is smooth with constant mean curvature. There exists a closed singular set so that outside of it, this guy is a smooth minimal surface. And this contains both the interior collapse region and the exterior collapse region. In particular, the interior collapse region is going to be a stationary varifold, okay? And the smooth minimal surface outside of these zero measure zero area singular set. And then there is the meager part. There you have nothing because the mean curvature is not locally constant, and then it's worse. And this is Allard, what Allard gives. Yes, so this I wanted just to explain where the Allard theorem enters into this. So the regularity of this problem is not Allard and then you are done. It's like Allard and then you have enough regularity to start creating competitors and try to understand something more. Okay. Yes, and then yeah, the other thing I had is the how you exclude the Y points. So I think I probably I went a bit fast. So and this is clearly a lot of information. So if maybe we could have some questions. Yeah, let me go to the page with the problems. Yes. So the transition region is a sort of free boundary because okay, it's not constrained by anything. I mean, it's okay. Yes, yeah. Okay, if you already know that this transition region is nice, like I don't know, C1 alpha curve, then probably you can also prove higher regularity of it. Actually, you can. Because, okay, that's a bit the point of this presentation. So this lecture is essentially the state of the art until 12 months ago. Okay, so then 12 months ago we had serious progress, and then more recently even more serious progress. But so, and this is what I will tell you tomorrow. So the transition region in the end will be nice, but at least the argument that we have, surprisingly, is not more varifolds. The argument is more sets of finite perimeter. So at the end of the day, it's like really when all these things are going to be proved, we will never use something like Vikramasekera theorem for stable varifolds or something super fancy. At the end of the day, you get away with a sharp regularity using Allard to get started, otherwise you don't get started, and using the Tamanini result for lambda minimizers. So what we will do tomorrow, I will introduce these measure theoretic reinterpretation of the Harrison-Pugh condition. So we are going to trade this beautiful condition that you can explain to a kid, okay, with something that it's horrible. So it's really like all the measure theory and some, okay, just to say what it means spanning. It's really ugly. But once you prove these two things are equivalent, so you're not changing the rules of the game, we will have something and that will make us able to do all these things with sets of finite perimeter. And at the end of the day, to anticipate something we will say tomorrow, why? So we are kind of getting in trouble trying to understand these. This is kappa. Here there is the horrible meager set, and here is E. Okay. And somehow the moral of the story is that you don't care about kappa and E, you just care about fixing a ball, I guess. And then there are three sets of finite perimeter. And using this measure theoretic version of spanning, we can prove that these sets are essentially lambda minimizers. And so when you see the regularity from their viewpoint, it's all fine. So this is funny because it's like, so the problem of doing these is really that this spanning condition is horrible to work with because it's extremely sensitive. It's like a closed set intersecting a curve. If you miss one point, you don't intersect the curve anymore and your competitor is not good to be used. Okay. So essentially we are creating a version of this condition that is stable under modification of the spanning set by sets of area 0. And then you're in business, because you can take, let me compare with a set of finite perimeter, and suddenly you can do that. So that's the thing where, but I mean, I will discuss more this tomorrow. But in a sense, the incredible thing for me is that at the end of the day, this looks like let's throw at it the fancy very false theorem. And I've been thinking about that for a long while. And then to solve another problem, we understood this measure theoretic version of the homotopic spanning. And actually, it makes working on this thing much easier. So, yeah. But you can't start this problem with my condition of spanning measure theoretic, because you're going to throw stones at me. So if I tell you that spanning means these, it's ridiculous. Okay, so I think this story must be told first with the curved spanning. Good? Okay. Well, I am. If you don't have, I mean, I talk about a lot of things, so.
Okay, so are there other questions or remarks? Okay, if not, let's thank Francesco. Okay, then I think we can start with the last lecture of today. Annalisa Massaccesi, she will talk about the Besicovitch 1/2 problem. Okay.
Thank you, Giovanni. Good afternoon. So yes, this afternoon, I'll try to keep things as light as possible, but I'd also like to tell you about some news about this very old Besicovitch's 1/2 problem. So it's not really news. The preprint was published online last year, but the problem is almost 1 century old, so the comparison is anyway. I've already made a seminar about these results in Pisa last year, and I think I messed up quite a bit. It was a Blackboard seminar, and so I hope to make up this time. So, an introduction to this very old geometric measure theory problem. What's Besicovitch's 1/2 problem? Let me start from the very beginning. The same problem, the same conjecture can be formulated in any metric space, but for the sake of understandability, today we will stick to R2, okay? So we are given a set E in R2, which is a Borel set, and we know it has one-dimensional Hausdorff measure, which is finite. And this setting, I will try to keep it as it is for the rest of my talk. Okay, so one thing that we can do with this Borel set is to try to measure the density of the set locally, but the density in general does not exist. So what we are guaranteed it exists instead is the lower and upper densities. So we start with those. What's the lower density? So we pick a point X in E, and we define the one-dimensional lower density of X at E as the lim-inf when these radii are shrinking of this ratio. At the numerator, at the numerator, we have the one-dimensional Hausdorff measure of the set inside a ball of radius R centered at the very point X, the one that we picked. And at the denominator, we have 2R, which is the diameter of this ball, radius R. So, okay, analogously, one can define the upper density of the point X in the set E as the lim sup of the same ratio. So if you think about a very common smooth case. Common is not the right word. Well, this upper and lower density, they always coincide, and they always give you the number 1. So imagine you have a smooth curve. You pick a point in the curve, sitting in the curve. You start with a blow-up procedure. So you intersect your set with balls centered at X with radius R. And, well, if the curve is regular enough, what you see zooming in is a diameter of this ball. So it coincides exactly with, it has a measure which coincides exactly with the diameter at the denominator of this ratio. Okay, so one thing that is rather easy to prove is that our assumption, the one that we made from the beginning, that the one-dimensional Hausdorff measure of E is finite, immediately implies the upper density to be less than 1 at almost every point. Why at almost every point of the set? Because, of course, you can consider also sets with crosses or non-trivial intersections. But yes, otherwise, let me say the upper density is the nice guy in this story. And in fact, we will lose interest in it very, very soon. I'd say immediately. Okay. What is the object, actually the regularity of this Borel set E we are interested in? The regularity that we want to focus on is rectifiability. So what is rectifiability? This set E is said to be one rectifiable, so rectifiable of dimension 1, if it can be covered by a countable number of images of C1 curves, these gamma and IN, so IN are intervals, and a remainder, some error, some ugly stuff, that has Hausdorff, one-dimensional Hausdorff measure equal to 0, so it's negligible. Okay, why rectifiable sets are so interesting? Francesco told us the answer yesterday, because rectifiable means that at almost every point we can perform a blow up, and at the blow up we see the tangent line to this set. Okay, so one thing that it is rather easy to see is that one rectifiability is equivalent to have density 1 at almost every point. This is the very basic version, the one-dimensional version of Price's theorem. And so this is a consequence of what I've said here and in the other slide, but if the one-dimensional Hausdorff measure of our set is finite and the lower density is bigger or equal than 1, then automatically the the set E is one rectifiable. So you start seeing that the interesting threshold is identified by the lower density being less than 1. If the lower density is bigger than 1, then we're perfectly fine. Okay, so here it comes. Let me go on with rectifiability. So one other thing that it's important to bear in mind for the sake of the techniques used in the result I'm going to talk about is this characterization of rectifiability. So one can prove that saying rectifiable means that at almost every point of the set, and for every epsilon, obviously, you can find a radius. This radius, in principle, depends on both the point and the epsilon you picked, and a closed connected set F in the ball of radius R0 centered at X, such that this set F covers, represents E in a very good way. So what is left outside the set F, the symmetric difference between E and F, can be estimated in its one-dimensional house of measure by epsilon times R0. Okay? So why I'm insisting on this proposition? Because you see that somehow when the one-dimensional house of measure of the set is finite, then there is a connection between being rectifiable and being covered by, not only covered, represented by connected sets. Okay, so there is a connection between rectifiability and connectedness. So this is only a qualitative property. So one-dimensional rectifiable set can be characterized as being big pieces of compact connected sets with finite length at most points and at a sufficiently small scale and with an error, allowing for an error. Okay, so what is important for the sake of this seminar is that if E is connected and the one-dimensional house of measure of the set is finite, then E is rectifiable. And now the Besicovitch's 1.5 conjecture comes. So you remember the threshold I showed you before here. So it's trivial to see that if the lower density is bigger or equal than 1, then the set is rectifiable. Can we lower this threshold? So this is the question posed by Besicovitch, and he was convinced that the answer is yes for a threshold which is 1/2. So a very smaller number with respect to 1. Okay, so his conjecture was that if you have a set whose lower density is bigger than 1/2 at almost every point, then E is countably 1 rectifiable. So we can, since this is still a conjecture, I mean, this is not a mystery. So we can rephrase the conjecture in this way. Take the set of indices sigma such that if the lower density of the set is bigger or equal than sigma at almost every point, then the set is countably 1 rectifiable. So we know, for instance, that the number 1 belongs to this set. Take the infimum of this set and call this threshold, really, sigma bar. The question by Besicovitch was, is sigma bar equal to 1/2? And well, yes, the answer is we don't know, but at least what we know is that sigma bar is less than 1. So the first result by Besicovitch himself in 1928, it was in the same paper where he stated the conjecture, was that we can go below the threshold 1. And well, he made this fantastic thing. He didn't say by a slightly little bit. He said because sigma bar is less than or equal to 1 minus 10 to the minus 2,576. So he estimated this number, and the paper is 1928. I will hugely talk about computer-assisted proofs today. He didn't have such tools, okay? Anyway, 10 years later, Besicovitch realized that actually we can do far better. He could do far better. So he proved that sigma bar is less than or equal to 3/4, so 0.75. And I'll show you why this 3/4 in the rest of the seminar. And 1 year later, one of his students, Dickinson, he showed that actually we cannot go below 1/2. So that's perhaps the reason why Besicovitch said this is a 1/2 conjecture, because counterexamples are available up to 1/2 if you go from bottom to top. Okay, and then more than 50 years passed, and David Price, together with Tisha, in 1992, they showed that, okay, you'll see the proof of the fact that sigma bar is lower than 3/4 is particularly clean, beautiful, neat, call it with a nice adjective that of your choice. So for these 50 years, people had this conviction, they were really convinced that 3/4 was the threshold, because, come on, it was so, yes, so neat. So what Price and Tisha, what they really wanted to show was that 3/4 wasn't the threshold. So they were just interested to go below, and they didn't bother to go really to optimize their proof. So what they showed is that, well, sigma bar is lower than this algebraic number, 2 plus square root of 46 divided by 12, which is more or less 0.73. Okay, but 6 years later, not in a paper, but in a master thesis work, one of the students of Price and Tischer, Alexander Schechter, wrote an optimization of the strategy of Price and Tischer, and showed that sigma bar is less than or equal to 0.72655 something, which is again another algebraic number, is the real solution of this polynomial of order 3. So 8s to the power 3 plus 4s to the power 2 minus 3s minus 3. And this is the only time in my life that I used Cardano's formula for real solutions of polynomials. So we were really happy to do that. Anyway, so this improvement is really just an improvement of the proof by Price and Tischer, or as Camillo loves to say, is Price and Tischer under steroids. And then our result. So together with Camillo De Lellis, Federico Glaudo, and Davide Vittone, we showed that sigma bar is below 0.7. Actually, it's even below 0.69, likely. But well, it was cleaner to write it like this. I'll tell you every detail about the digits of the number later in the talk. Okay, so this is the state of the art. Since today I have a little bit of time, I'd like to open a parenthesis on the counterexample of Dickinson, so that we see how it works, this set, which is purely unrectifiable. It has density exactly equal to 1/2, so upper and lower density, they coincide, and perhaps I'll be able to convey the idea of why 1/2. So the counterexample by Dickinson is the following. It is a graph. The set E is a graph in R2. So imagine we start defining this family of functions Fm, so M is a positive integer number. Depending on the variable x, here I made a mistake because I called x a variable instead of a point in R2, so sorry for the... and then we start building these functions which are piecewise constant. So if you pick, for instance, f1, it's a function with values 1/2, -1/2, 1/2, -1/2. And then if you pick f2 is 1/32, -1/32 in intervals which are smaller and smaller. Okay, and then you take S of x to be the series. You add up these functions fm, and you take as a counterexample the graph gamma of this function f, and I'll show you a picture now, but what Dickinson shows is that gamma, is purely rectifiable, and the lower density is exactly 1/2. So why? This is f1, okay, in the interval 0, 1, so 1/2 - 1/2. And then you have f2, which is way smaller. And then, I'm sorry, but do you see these green small segments? This is f3. If you sum just f1, f2, f3, what you get is this blue wavelets you see around the red segments, okay? And remember, this is not the picture of gamma, it's just an approximation. In Dickinson's construction, you keep going on. Okay, so what's the point? This is a zoom around the red line in such a way that you see the small segments going up and down. Okay, so how can one see that the lower density is equal to 1/2 for almost all points? Well, the estimate from below, so the fact that the lower density has to be bigger than 1/2 is kind of easy, because pick an epsilon, then for sure you'll find an n such that the difference between the very function and the approximation at step n is very small. You can see it also in the picture. Let me show the picture. So you see the difference between the segment and the little wavelets is, they are not wavelets, they are segments themselves, but it's very small. Okay, so for sufficiently small r, sorry, there is an r over there, you can see that the one-dimensional Hausdorff measure of gamma intersected with a ball of radius r centered at A is at least r. So if you take this down, it's at least 1/2 minus a small error. And on the contrary, the lower density is smaller than 1/2. Here you have to be slightly more careful, but you can show, roughly speaking, that almost every point of gamma, for almost every point of gamma, you can imagine you're here, okay? For almost every point of gamma, you can find an infinite number of segments, of reference segments, such that you are at the far right of one of these segments. Okay? only the horizontal distance counts, because vertically we have the estimate we had before. So this happens for infinitely many segments. It means that at the right scale, the picture is exactly the one that you're seeing here. So your point A is not only the center of your ball, but one of the extremals of the radius of this ball, and thus the quantity of the set gamma inside this ball is, the ratio is exactly 1/2. Okay, so this set has lower density exactly 1/2, which means it cannot be rectifiable, because otherwise it immediately jumps to the threshold 1. Okay, so this is Dickinson's counterexample. So now let's open a second parenthesis about the quantitative Besicovitch's 1/2 conjecture, and then we talk about the proof. So there is a conjecture, we called it the quantitative Besicovitch 1/2 conjecture, which is not, neither implies nor it is implied by the original conjecture, but well, it's quite similar, and it says the following: take S bigger than 1/2, then you can find positive constants through parameters epsilon and delta with the following property. If E is a compact set such that these two properties are fulfilled, then if you take any two connected components of the set E, they are at least delta far apart. And these two hypotheses should recall the setting of the Besicovitch's 1/2 conjecture. In particular, we're asking that given any Borel set U, the one-dimensional Hausdorff measure of E inside the set U is less than or equal to, up to some error, the diameter of U, okay? And so this is a relative of having one-dimensional Hausdorff measure which is finite. Okay, the quantitative relative of having finite Hausdorff measure. And this is the relative of having lower density bigger than sigma. And it says that pick a point X in E, pick a radius which is smaller than 1, this is scaling invariant, then the one-dimensional Hausdorff measure of E intersected with the ball of radius R centered at X is bigger than or equal to 2 sigma R. So take the 2R at the denominator and you get the ratio defining the lower density. Okay, as I was saying, yeah. Yes, but since you're doing it at the blow up, it means you're not waving around. Okay, so, but what's the relation with the original conjecture? In the original conjecture, we had finite one-dimensional Hausdorff measure and lower density bigger than sigma. Then what can be proved starting from these assumptions is that at almost every point and for every epsilon, there exists a radius depending on epsilon and the point, such that A holds, okay? And this is true for every radius under R0, smaller than R0. Okay, so they are related, but not really the same conjecture. Now, why did I open this parenthesis? because now I want to show you what is Besicovich's one argument to get 3/4. And it's better, for the sake of drawings, to pass to the quantitative conjecture. Actually, what we'll do is the following. We will replace the original assumptions of the Besicovich's 1/2 conjectures with the quantitative assumptions. And then we will show that if sigma is bigger than 3/4, these assumptions imply E to be connected. And this, if you have in mind, if you remember the connection between connectedness and rectifiability, in the end gives you the rectifiability of it. So now what I want to show is this implication. In every version, Besicovitch's, Price-Tischer, and a hint of ours. Okay, so what is Besicovitch's argument? So we're starting from those assumptions, and it's a proof by contradiction. We assume by contradiction that there are two non-empty sets, E1 and E2, which are, say, connected components of E. They are distant from each other at a positive distance, say E1 and E2 without loss of generality. They can be taken as compact sets. Their positive distance, we call it R. And then we pick the 2 points, x1 belonging to E1 and x2 belonging to E2, that realize exactly the distance between these two sets, these two components. Okay, and then we take two balls. The two balls are centered respectively at x1 and x2 and have radius exactly r, the distance between x1 and x2. So the picture is precise. And since the two sets are far apart, this almond-shaped space, the intersection of the two balls, is empty. There is, there is no E inside this intersection. Okay, this is very useful because then we use the following trick. We take a third ball, a ball which is centered in the middle point between x1 and x2. So it's x1 plus x2 divided by 2. And it has radius 3/2 times r. So it's this, this, and this. Okay, it covers precisely the union of the two smaller balls. Okay, but we said that E does not intersect the intersection of the two small balls. So if we measure the one-dimensional Hausdorff measure of E inside the big ball, the one with radius 3/2 times r, what we have is something bigger than or equal to the sum of the amount of E which sits inside the first ball and the amount of E which sits inside the second ball. Okay, and now on the left-hand side, we can use the first assumption. So we know that the one-dimensional Hausdorff measure of E inside this ball, which is our S, sorry, is smaller than the diameter. The diameter is 3r. On the right-hand side, we have that the second line. So each of these balls has this estimate. So what we get here is twice 2 sigma r minus epsilon. Okay? But if sigma is bigger than 3/4, this is a contradiction. Okay? And it's done. So probably one can also guess why so many people for 50 years were convinced that 3/4 is the threshold. Because it seems like a proof that cannot be improved. Very geometrical one. Actually, all the proofs of this seminar will be very geometric. Okay, let's try instead to go further. So we are in the same setting. So we keep this simplified version, these assumptions as our assumptions. Still, we want to prove that E is connected, but we want to improve sigma. So we want to say, okay, perhaps sigma was lower, smaller than 3/4. We want to see if we can do something better, okay? So the setting is the same. We have E covered by two compact sets, E1 and E2, which are at some positive distance. And without loss of generality, we decide from now on that this distance is equal to 1, okay? There are these points, x1 and x2. What happens? Then there is this very nice lemma saying, okay, either the one-dimensional Hausdorff measure of E1 inside the ball centered at x1 of radius r is smaller than more or less r plus 1/2, or it has to happen for indices, for the index 2. Okay, so the picture is more or less the following. We have x1 and x2. We have this distance, which is 1. Okay, and then we have 3/2, I guess, is this one. So a slightly smaller ball. There is this one, and there is this one. So, okay, either the left ball or the right ball have very few of E1 or E2 inside it. Okay, so the big mass is concentrated on the other side. And the proof is again by contradiction. So assume it doesn't happen. So there are radii R1 and R2 such that this inequality is not fulfilled. Then we measure the one-dimensional Hausdorff measure of E intersected with the union of the two balls. And this is bigger than 1 plus epsilon. And then we have here R1 plus 1/2 and R2 plus 1/2. So we get this. But this is bigger than the diameter of the union of the two balls. Okay. This one, and this is a contradiction. So, okay, the lemma is true. And with this lemma, if you want, you can prove Besicovitch with 3/4 again, but it's an asymmetric version. So it's useful because this is our starting point. So we assume R to be equal to 1. Then let's say the first inequality holds. We can pick one. Let's say it's the first one. Then we have that the one-dimensional Hausdorff measure of the set E1, which is this one, inside the ball of radius 1, this, is less than or equal to 3/2, 1 plus epsilon. But E1 and E2 are 1 far apart. So the intersection of the ball centered at x1 with radius 1 with E1 coincides with the intersection with the whole E, because there is no E2 in that ball. And for that, we can use the usual assumption on the lower density. So this is bigger than or equal to 2 sigma times 1. So it's 2 sigma. And again, if sigma is bigger than 3/4, this chain of inequalities fails. Okay, so this is the asymmetric version. So how the argument by Price and Tischer goes on. So let's forget about epsilon because it's around, but we forget about it. This is the previous setting, okay? So we decided we're in the case in which the ball centered at x1 is the important one. And we made this proof by contradiction. Okay, the point is that perhaps if sigma is lower than 3/4, this is not a contradiction, right? But it still tells us a lot. Why? Because it's saying, so now it's asymmetric, so I can draw x2 very far and x1 center stage, okay? And then we have this ball of radius 1, okay? X2 is exactly here. Okay, so we know that E2 is all outside of this ball, the part E2 of the set, and inside this ball there is only E1. Okay, so something. Fine. So let me, I will rename in a moment x1 with p1, but it's just for the sake of. Okay, so we said we didn't reach a contradiction with the chain of inequalities above because sigma is perhaps smaller than 3/4. But saying that the diameter of E1 in the ball centered at x1 of radius 1 is bigger than 2 sigma means that there are 2 points, P2 and P3, inside E1 and the ball, which are at least 2 sigma far apart. This is just the definition of the diameter. So there are 2 points in E, P2 and P3, which are at least, these are 2 aligned. I have to take care of the alignment, which are at least 2 sigma far apart. Okay? Okay, and now we play the following game. So we pick the 3 points. Now x1 is renamed to be P1, okay? And we take, so the following 3 points, P1, P2, P3. And we take the balls of radius 1 centered at P1, P2, P3. Okay, so since all these points are very far from E2, what we see inside these balls is exactly E. Okay? We can't see E2 anymore. Okay, so we have these balls. Okay, x2 is far, and we have these 3 balls. Okay, and now we try to inflate these balls, meaning that, well, we look for radii, okay? 3 radii. R1 is, okay, or R of P1, R of P2, R of P3. In such a way that the balls centered at these points, P1, P2, P3, are still pairwise disjoint, okay? So 3 balls, pairwise disjoint, okay? And we define UPR to be the union of these balls. So this, union this, union this. Okay, and now we also consider the big ball. So the one that it is a ball shaped. Actually, we are in R2, so it's really a circle. It is, and it contains, it has a radius which is big enough to contain these small 3 balls. Okay? Okay. What is happening with this kind of construction? Perhaps the one in the slide is better than what I made at the blackboard. So we want to see what is the one-dimensional Hausdorff measure of E inside the big ball. Okay? Well, these balls are pairwise disjoint, so we can take the sum over the 3 points, P1, P2, P3, of the one-dimensional Hausdorff measure of E1, because E2 is too far from us, intersected with each one of these balls. Okay? And now we use the the assumption in the first line. So we know that this measure has to be less than the diameter of capital U, because it was the assumption on the first line. Moreover, because of the slick lemma by Price and Tischer, this is also smaller than capital R plus 1/2. Sometimes it is useful. I mean, we take the lowest between these two, and we cannot avoid it. Sometimes it works because of this, sometimes it works because of that. Okay, but on the right-hand side, we have the assumption on the second line, saying that this measure for each of the small balls is bigger than or equal to 2 sigma. The sigma is the lower density. So 2 sigma times the radius. So you get the sum. Yeah. This is working on symmetric spaces. Yeah. So what we get is this is less than or equal to this one. If we are able to unbalance, to get a contradiction from this inequality, we're done. Okay? Which means we transformed our Besicovitch 1/2 problem in, okay, I can't use the, in a Apollonio problem. Okay, a problem in placing balls in smart ways in the space. Okay, and if you have 3 points, P1, P2, and P3, you can make the computations by hands. You get the polynomial, the third order polynomial I showed you before. You get the precise numbers, and you also get two optimal configurations, which make your inequality fail, means it's a proof by contradiction, if sigma is less than or equal to 0.772 and so on and so forth. The solution of that polynomial. So the solution is the following. So P1 is the center, the origin. And then you have P2 and P3, for instance. Then this is the ball of radius 1. So E2 is in here. And you can choose between these two families of balls. Either the blue one, which is empty ball of radius 0 at the origin, and the two blue balls here. And the set of balls too, so the 3 red circles. They give you exactly the same number. They are both solutions, and actually this radius coincides with this radius, and this radius coincides with this radius. Okay, you can choose. Anyway, what you get is Price-Tischer's result. Let me observe that you want this inequality to fail. So it's important that you choose this radii to be as big as possible. So the radii, you have to inflate your balls, okay? It's important to have this radii as big as possible, and then you have to study this inequality for all the possible families P, the positions of the points P. So already in this easy 3-point setting, it's a min-max problem, okay? you want to maximize the radii, but you have to take the infimum of the difference on all the possible families of points P. Okay, so now we want to push this construction further and further. I mean, you remember we started from Besicovitch, okay? Let me go back. Okay, we started from Besicovitch, which had basically 1 point, the origin, what we said it was the origin in the end. And then we said we can go further because if the inequality is not false, if the inequality still holds, then we can produce like 2 children for our origin, P2 and P3, which are at least 2 sigma far apart. And then we try to cover these 3 points with balls which are as big as possible, not intersecting, and so on. So the basic idea of our proof is nobody prevents us from going on. So say sigma is smaller than 0.72 and something. So this is not a contradiction, but we can force P2 and P3 to produce 2 children each, okay? So it's a very complicated family issue. So this is the idea. We go on with producing points, bad points, which are, if you want, we want a rectifiability result. We want to show that the set is rectifiable. It's a proof by contradiction, and indeed what we're doing is saying, okay, assume it's not rectifiable, then I'm showing you that the set E is very sparse. It's scattering all these points, producing all these children all over. Okay. Yes. Because, okay, this to get, oh, sorry. In order to get this, it's 1 afternoon computation. But when you start going on with the number of points, it easily gets impossible. I'll tell you about the times, the computational times in the end. So let's go for the actual proof. So here we have the hypothesis of classical original Besicovitch's 1/2 problem conjecture. The idea by Price-Sticher is to define this Besicovitch pair condition of index sigma. Okay, so you are in a metric space, and you say that the metric space satisfies the Besicovitch's pair condition for a sigma that at these points ranges between 1/2 and 1. If for every choice of a Borel measure mu, which plays the role of the set E, now we want to see that mu is rectifiable, which has this bound mu of S less than or equal to the diameter of S. So it should recall you the first line of our assumptions. There exists a proportion tau such that for every lambda there exists a delta such that if there are 2 sets E2, E1 and E2 in well, it's below, which are at positive distance between 0 and delta, and mu of the ball centered at X with radius R is bigger than 2 sigma R, so puts this 2 at the denominator, you get the definition of the density for the measure mu. For every X in the union E1, union E2, and for every R. Then, every time you take an open set U which intersects both E1 and E2, and you take out E1 and E2 from U, what you see is still something slightly big. It's tau times the diameter of U. So this is the way to translate the assumptions of the Besicovitch 1/2 conjecture, sigma conjecture, in quantificators, in for every exists, for all. Okay, for any metric space is only a positive number. If you do it in the Euclidean space, you can also say what is tau. So the proposition, which is not as crazy as it may seem from the definition of the Besicovitch pair condition, is that if the Besicovitch pair condition holds for an index sigma, then sigma bar is less than or equal to sigma. So you have to check the Besicovitch pair condition, and then automatically you have an estimate on the conjecture. So what we said is that, well, we defined a function, the objective function, which is called min m sigma of this, of this variable L. If this objective function, this L is just because we lack of compactness, okay? We don't, it's just a radius to close up, to enclose our problem. If the objective function is strictly positive for some L, which is then the Besicovitch pair condition holds. And if the Besicovitch pair condition holds, we have that the threshold is an admissible threshold for the Besicovitch product. So how it is defined, the objective function? I will define it step by step, showing you the analogies with the constructions the geometric constructions I did before. So this has to be defined. I know I said nothing, just saying, okay, there is a function. If this function is positive, we're done. Okay. Yes, and moreover, in R2, as you were asking, delta can be taken to be equal to lambda, and tau is explicitly found. Okay, so we do. So we want to build a function such that this theorem holds. Okay, and this theorem will hold for a proof by contradiction. So by contradiction, we assume the Besicovitch pair condition does not hold. That is, there exists a measure with all these assumptions. So it has the estimate on the diameter, the two components which are far apart, the estimate on the density. But for every capital U, we have that U intersects both E1 and E2, but this inequality is reversed. Okay, so there is this measure mu failing the Besicovitch pair condition. So without loss of generality, E1 and E2 are compact. We assume the origin to belong to E1, and for instance, -1, 0 to belong to E2, and the distance between the two sets is exactly 1. Okay, the problem is scaling invariant. And then we assume the usual, that is that mu of a ball centered at a point X, which is in the support of mu with radius R, is bigger than 2 sigma R. Without loss of generality, because of the slick lemma by Price and Tischer, we can also assume that mu of E1 is less than or equal to capital R plus 1/2. Do you remember this little lemma was either E1 or E2 has one of these inequalities? Okay, and now we play the usual game on all the points P which are relevant for the problem. So if you have a set of points P, you start defining capital U of P and R as the union of balls which have center at P and radius, some radius. And capital R of the same pair, capital P and R, is the smallest radius that allows the ball centered at the origin with radius capital R to cover the whole capital U. It's precisely the same setting as before, but before capital P was 3 points, P1, P2, P3. Okay, and now choose a family of points P which belong to E1 and a sufficiently big ball centered at the origin. And the choice of radii has to be made in such a way that the balls are pairwise disjoint. And then we do the same, which means we want to measure mu of the union of these balls. These balls are pairwise disjoint, so it's the sum of mu of each of the ball intersected with E1. For each of these balls, we have an estimate from below of the measure, which is 2 sigma times the radius of the ball. So we have this. Just neglect epsilon P for a moment. So imagine we got this. On the left-hand side, we have that this measure is nonetheless smaller than the diameter of capital U because of this, and capital R plus 1/2 because of this, or because of the slick lemma. So if we're able to make this inequality fail, we're done. So we define in this way our objective function min m sigma, okay? So we start step by step. So first of all, define F sigma, depending on both the family of centers of the balls and R, to be this minus this divided by 2 sigma, okay? So this inequality fails if this quantity is bigger than 0. Okay, and then, as I was saying before, one thing is in our power. We can inflate the balls. So we can take the maximum among all the allowed radii, such a way that the balls are pairwise disjoint. And this is the function m sigma. But m sigma is still depending on the family of centers, the family of P. You take the maximum among all the radius. Yeah. Okay, so F sigma is just the rearrangement of the formula, the thing that we want to be bigger than 0. Then M sigma, so we have 2 variables, capital P, the family of centers of the balls, and R, which are the radii. So M sigma of P is the maximum, the optimization on the radii of the balls. Yeah, of course. I mean, taking the maximum, this is a linear problem, so it's not difficult. The problem is when you do the other step, because now you want to get rid of capital P, the family of points. These are points in the support of the measure mu. Who knows what is happening on them? So we have to take the minimum of M sigma, which is a minimum with a constraint. So P has to be this sigma L stable, which means that for every P in the family capital P, and for every R, and this is very important in this range, we can produce two children, Q1 and Q2, which are at least 2 sigma R far apart. Okay, so in this minimization part of the optimization problem, we have a constraint, which is the family capital P has to be one of this family, this big genealogical tree family. It's like a soap opera. Okay, so now I hope you're convinced that if we can compute min m sigma and min m sigma is bigger than 0, we're done. The Besicovitch pair condition holds, and we have an answer to the problem. Now the real problem becomes, how do you compute min m sigma? I mean, we can do it when P is just 1 point, 3 points, and then we're lost. So a possible discretization of this problem is to introduce one min m sigma. So it seems really unharmful, innocent, to have this for every R in this range, you can produce 2 children, which are at least, it's not. So a simplification of this objective function could be having a constraint saying for every P, I can produce 2 children, which are exactly 2 sigma far apart. Okay, I don't care about this R between 1 over lambda and 1 over L and 1. So this is a way to simplify the problem. And this is something we can hope to compute at least theoretically. Because this one min m sigma can be discretized, but the important information is the following, that one min m sigma is a lower bound for min m sigma. So if we prove that one min m sigma is bigger than 0, also the original objective function is bigger than 0, the Besicovitch pair condition holds, and everything. Okay, so we focus on one min m sigma, the one with the children with less children. And we produce a hierarchy of objective functions. So these objective functions are a way to discretize one min m sigma at every step starting from 0. Yeah. No, it's not. No. No, it's not. No, I said it's important because otherwise you do nothing with one min m sigma. No. It's crucial because at least it's a lower bound, but it's not obvious. Okay, so discretization of one min m sigma. First step, in the family capital P, you just put the origin. Okay, that's Besicovitch's proof. And well, it's as simple as then it's a definition, it's a recursive definition. So once you have f sigma k minus 1, you produce the next objective function in this way. You pick the previous family P, you ask each point to produce 2 children at distance exactly 2 sigma. So it's not so many points. Picking P in the previous family, and the 2 children have the constraint that you already know. So if you want to follow from the sketch, from the geometric proofs I told you before, it was origin, F0. And then, so Besicovitch. And then Price-Tischer was 3 points, 0, and its children, P2 and P3. So the next layer, say F sigma 2, means origin, P2, P3, and 2 children each. So it's 7 points. Already 7 points is a mess. So the interesting thing is that this is a way to discretize the objective function, meaning that if you get from some k that k1 min m sigma, so the k iteration of f sigma is bigger than 0, then then 1 min m sigma is bigger than 0, then min m sigma is bigger than 0, then the Besicovitch pair condition holds, then you have that sigma bar must be less than or equal to sigma. Okay. So the problem now becomes compute k1 min m sigma. So with this hierarchy, no, I don't know if it's not the correct spelling of hierarchy. K equals 0 coincides with Besicovitch's argument. K equal 1 coincides with Price-Tischer's argument, the one under steroids. What about 2-1 min m sigma? You can try to compute it. The problem is that you have, not by hands. It's impossible. I mean, it's, how many? So you can assume, it's 7 points, but you can assume, so 7 points means 7 radii. So it's a maximization in the min-max problem of 7 radii. But the 7 radii have to be found for each configuration of the 7 points. The 7 points have 2 coordinates each, apart from the origin, which is the origin, and you can pick P2 to be on the y-axis, for instance. So it's 12 parameters, or how many? 11 instead of 14. So already in this case, it's too much. And the problem is that you have to feed the computer with the sigma, and then it goes and goes and goes for days, and it says yes or no. Okay. So that's why we said, okay, 0.7, we checked it and it works. 0.698, I think, we checked it and it works. And then we got both. I mean, we didn't go further. So M sigma P was the maximum, so on the family of problems. It was just inflating the balls, okay? And it's a maximum on a finite number of linear programming problems because it's just the optimization of the radii. So there are very fast routines to compute them, fractions of seconds, okay? There are ORTools library for Python, C++. You can download them, ask Gemini to help you implement the thing because we're not really good at programming, and it goes. Other good news. One could think, okay, but this is a computer-assisted computation. How do we make a proof out of this? The point is that actually M sigma is Lipschitz. So you have a control on the error because of the Lipschitz function, because of the Lipschitz cap. So yes, the computer is doing a discrete test, but anyway, if the mesh is, if the points where the computer does the check are close enough, you have the Lipschitz constant, and you're okay. And okay, yes, there are clever ways to improve a little bit the computation, like getting rid of some parameters because you take 1 point to be the origin and so on. These are the good news, and they end here. And then there is the list of bad news. So K1 min m sigma, they require to solve. So you pick capital K to be the number of points around. So you sum all the generations. Okay, so you get 2 to the power k plus 1 minus 1. And if you want to solve k1 min m sigma, the number of linear programming problems, each of these problems takes a fraction of a second, but the number of problems is k to the power 2 divided by 2 plus k times 2 to the power k. So it's hugely exponential. So without improvements, without smart solutions, just to solve 1 min m sigma, one needs 30 microseconds to compute min m sigma p and 300 million years to conclude the computation. So yes, with improvements, cutting down parameters and so on, for k equal to 2, at the beginning, it took a laptop like this, one of our personal computers, more or less 5 days. The first time Federico forgot to plug the battery, the electricity. So after 2 days, the computer, yes, it was out of battery, and well, we redid it, and it was 5 days. 5 days. Now it's better. Emanuele tried the code on Leonardo, and it took 1 hour, you said, but it was way faster. Anyway, 3.1 min m sigma is out of reach. For the moment, we can't even think of analyzing that, because it would be 7 plus 8, 15 points, and it's crazy. Already having 7 or 6 points made a huge difference between 6 and 7. So when we decided that, okay, one of these points is the origin, it made a huge difference. Okay, and now theoretical limits of the proof. We know, because we tried, that 2.1 min m sigma is equal to 0, so the proof fails. It's not bigger than 0. If sigma is 0.683. Okay, that's not tragic. I mean, one can guess that it's a 2.1 min m sigma. It's a huge simplification of the original min m sigma, the objective function. So, more seriously, we know 1 min m sigma, which means allowing only children at a fixed distance of 2 sigma, fails when sigma is 0.64368. And this is not because we tried it with the computer, obviously, because we cannot compute 1 min m sigma in its whole complexity, but because you can produce a family of points with these distances, which make the parent-children relation fail. And it really is a soap opera, because at a certain point, the fathers are children of the children. It's something gross. But you see, if you take one of these trapezoid and these distances are 1, these sides are 1, and the diagonal is 2 sigma, you start with this crazy loop. The rather magic thing is that even this threshold is an algebraic number. Who knows why? So the only hope to 1/2, if you believe that 1/2 is the correct number, the correct threshold, is to be able to compute min m sigma. And this, for the moment, is crazy. But I want to conclude with just one picture, which seems so we tried to tell the computer, okay, start from the origin, then produce children when you're almost at the threshold. Let's see what happens. And well, what happens is that these points are really scattering. So even, and not scattering, it's the contrary, sorry, I picked the wrong word. They are aligning somehow. So who knows? I don't for the moment, but I thank you for your resistance and your attention.
So maybe I'm wrong, but it's the problem is so somehow that if you would have more powerful computer, you could improve the estimate some point, or
till this
kind of
till this point, till this.
Okay.
Because one minimum sigma is something that, provided you have infinite computational power,
Yes.
you can implement in a computer. But minimum sigma, no, because there are possibly infinite points.
So even if theoretically infinite power of computation, you cannot go at the moment below this threshold.
One of the ideas, I think it was David Bate that suggested it, was why don't you try to discretize in a different way? For instance, because at a certain point you have to surrender, to give up to a discretization. So one of the suggestions I got, sorry, it's very slow, okay, was, okay, so the problem is passing, the problem of being able to implement this computation, which is the one you would like in a computer, is this for every r in the range instead of just r equal to 1. So here we just picked r to be equal to 1. What happens if you do it for r equal to 1, r equal to 1 minus something, and r? So you discretize also on that, in this interval, instead of choosing just r to be equal to 1. It could be the complexity in that case was crazy, but it could be one attempt.
Thank you.
Hi, thank you for the very nice talk.
Thank you.
So I don't know if it's a reasonable question, but is it mathematically sensible to expect that the infimum, to approach to prove that the infimum is not a minimum? Do you know that already? I mean, for the sigma bar, that's what I mean.
For the sigma bar, what do you mean?
So because, I mean, so you go to...
But in the conjecture, you ask, in the original conjecture now, you ask that the lower density is strictly bigger than the threshold. So...
Okay, so it doesn't hold for the...
No. In fact, Dickinson has...
Yeah, right. Right, that's what I was... But even when you find the infimum, you know it doesn't hold for that guy.
Yeah.
Okay, all right. Okay, and the second question was, do you know the minimum sigma, how close it gets to give you the answer? I mean, because it's just a lower bound still, no? Or do you know it's exact?
No, it's just an implication. The Besicovitch pair condition implies that threshold to be good. Okay.
So, I mean, if you could solve it with the
Yes.
M sigma, then would you solve the full question? That's the question.
Yeah, I understand. I don't know.
Okay.
We hope
Right.
so, but actually the Besicovitch pair condition in min M sigma positive means Besicovitch pair condition holds. This is for sure. But you don't know if the Besicovitch pair condition is equivalent to have that sigma.
Okay.
It's just an implication.
Right. Thank you.
Thank you. So in the hierarchy that you are doing, is there any chance that the minimizer, for instance, for the 2m min M sigma, has any relation with the 1? Like, can you start from almost minimizers of the 2 problem?
I don't know. I don't know. And I think we tried. So we initially tried to say, start from the configuration. Where is it? The one with red and blue circles. And from there, try, but I think it failed. If I remember correctly, it failed.
So if I remember correctly, you proved that 2 min m sigma is 0 for 0.683.
Yes.
But did you do it still with a computer-assisted proof?
Yes, we asked and it said it's 0.
And okay, because it seems harder to prove with a computer-assisted, with a computer that something is 0 either than rather than it being greater than 0.
Yes, but I think that we really got something like negative.
Okay.
With plus the Lipschitz control. It's this you're referring to.
Yes.
I think we got something that was like negative or something.
Okay. Thank you.